everyone is doing well today. My name is Jessamine Cox. I am the EBC's Operations and Programs Coordinator. And before we hand things over first to Frank Riccardi to talk a little bit about the Environmental Business Council, and then to Jaana, one of our program chairs, to introduce the program, want to make sure that everyone is well set up for today's webinar. So first thing, if you are sitting and looking at your screen and you realize, oh my Zoom video is not actually who it says I am. Sometimes this happens if your daughter has hijacked your Zoom. What you need to do is just find the Zoom toolbar, click on the participants button, and then a new bar will appear on the side of one of your screens. Hover over your name, you'll see 3 little dots appear, and then you'll have the editing capabilities to update your name and also importantly to put in your organizational affiliation. That really helps everyone get a clear sense of who is on the call today. We also do recommend putting your screen into side-by-side view. There's a couple of ways to do this. One option is shown here, where you just need to find this little drop-down bar, also located near your Zoom toolbar, and make sure that you are putting your screen into side-by-side view. That really helps during presentations, as you're then able to either adjust the side of the screen that has the presentation to be a little bit bigger, or the side of the screen who has the person speaking to be a little bit bigger. We do also recommend putting your view into speaker view. This really helps when we do get into our moderated discussion. Rather than having things be in gallery view, which is more of a Brady Bunch type configuration, if you have it in speaker view, Zoom automatically makes the screen of whoever is speaking at that point in time the biggest on your screen. So especially when there's some back and forth between a lot of different people, as there will be during our panel discussion, it's helpful to have this set up. And you can also get this set up during presentations to have it be speaker view and then have the view be side by side with that presentation as well. It looks like someone already activated this today. So if you also would like live transcription, this is found as an option within your Zoom toolbar. All you need to do is click on this. This slide might be a little bit outdated. I think you just need to click on this, choose English as your language. If you run into any technical issues, we have a chat function. So there are 3 EBC staffers currently on the call, myself, Jackson Bailey, and Stephanie Sukar. There is, as you see in the screen here, a direct message function. So if you run into any issues or do have specific tech questions, please don't hesitate to direct message any of us. But for the rest of the presentation, as you think of questions, please go ahead and pop those questions right into the chat. This will provide us with a running log of questions throughout the full duration of the webinar. Our moderator and program chair, Liz Denley, who selected the fantastic tunes we kick things off with today, will be keeping an eye on the chat function. And as time allows, we'll try to direct questions here and there to our speakers towards the end of their presentations. But otherwise, we will hold the majority of questions to the panel discussion at the end. So that makes it extra important that as you think of your question, don't lose your train of thought, just pop that right into the chat. So with no further ado, I will turn things over to Frank, who will tell us a little bit more about the benefits of becoming a member of the Environmental Business Council. Frank?
Excellent. Thank you, Jessamine. Good morning, everyone. Amazing turnout for today's seminar. Very important topic, PFAS in air. I think everyone is aware of PFAS and other environmental media, and it'll be nice to learn more about PFAS in air and some of the issues we deal with on a day-to-day basis. So I'm Frank Riccardi. I'm with Weston and Sampson and chair of the EBC PFAS, our Emerging Contaminants and PCB subcommittee. I'd like to thank our sponsors for this seminar, Ramboll and Tech Environmental. Thank you all for sponsoring and for supporting EBC. It's very important for us to bring these seminars to you, and your support makes it very easy to do that. And what are the many benefits of being an EBC member? EBC is really the venue. It's really the forum for our industry. We are throughout New England. We have many programs. As you know, if you get the weekly update, if you don't, please sign up and become a member. There are many benefits. I've seen it firsthand with leadership development as folks go from ascending professionals into committee chair roles. It provides access to many different decision makers, regulators, clients, fellow colleagues. shareholders or stakeholders, and it provides a lot of professional development for your staff. Great networking to meet other colleagues and potential work relationships through the networking, and a lot of exposure to different industry issues as we go through and grapple with some of the issues of our day. So there are many, many benefits, and it's a great forum for our industry. There are many different committees for whatever you choose to get involved with. EBC does an excellent job of making sure that the committees are dealing with the issues we have on a day-to-day basis. And if something is not here, we add it. Specifically, the TSCA and Emerging Contaminants Subcommittee was added about 10 years ago, and then we expanded to Emerging Contaminants about 5 years ago. And, you know, if there's something on here that you don't see that you have a particular passion for and you want to lead a subcommittee, please contact EBC, Jessamine, Jackson, or Ann. And the state chapters are Connecticut, New Hampshire, and Massachusetts to cover North, Middle, and South. Thank you. So this seminar is brought to you by the EBC Emerging Contaminants Working Group. Liz Denley is the chair of the working group from TRC. The working group leadership team is Annie Lou DeWitt, Jeff Hirschberger, Steve LaRosa, Jim Accolini, Jaana Pietari, and Jason Wilkinson. They do a great job developing these programs and seminars for EBC. Thank you all. So upcoming programs, tomorrow, if you haven't had enough PFAS, we have another program on PFAS occurrence and mobility potential in soils and biosolids. On June 15th, we'll head into the PCB realm and look at PCBs, indoor air update, where have we been and where are we going. June 22nd, if you're sick of PFAS and PCBs, I don't know how anyone could be, but there's other talk of emerging contaminants, the best of the rest. And July 13th, a hybrid seminar, so in-person and remote, is the Emerging Contaminants Working Group, the program planning meeting. And if you're listening to this and you'd like to be part of the planning and the subcommittee, please let us know, and we will have that as well. So finally, presentations and recording will be shared with all the attendees, so you don't need to take a lot of notes. We'll have the information available, as well as contact info for speakers and moderators on the agenda. As Jessamine discussed, please use the chat feature to ask questions. And if you are not a member, please consider joining. It is a great, great organization and a lot of fun. EBC is a great forum. All right. So without further ado, I'd like to introduce one of our Emerging Contaminants Working Group members, Jaana Pietari. She is program chair for this seminar and a senior managing consultant from Ramboll. Jaana.
Thank you, Frank, and thank you, Jessamine. And welcome also from my behalf to the PFAS All Things Air webinar. And I'm really glad that we have a great lineup of speakers today who will be sharing their insights and covering quite a bit of ground today on this important topic of PFAS in air. So you will gain insight into technical challenges specific to PFAS air quality and about the current and future PFAS regulations in air. We will also hear about gas phase transformations of PFAS and about lessons learned from PFAS ambient air monitoring program. We'll also hear from USEPA whether PFAS should be a concern for vapor intrusion. And then finally, we will learn about potential issues associated with the analytical methods related to PFAS in air. And after all the speaker presentations, there will be a panel discussion with all of you, and that will conclude the webinar. And my co-chair, Liz Denley, will be moderating that discussion. So with that, I would like to introduce our first speaker, Matt Traister. Matt is a vice president with Ramboll and has more than 3 decades experience in environmental consulting, including air quality, fate and transport, vapor intrusion, and more recently, emerging contaminants. Matt's topic is evolving technical issues with evaluating PFAS air quality impacts and the current future state of regulations. With that, welcome, Matt. Thank you, and the stage is yours.
Thank you, Jaana. Good morning, everybody. I am absolutely thrilled to be a part of this webinar. I have spoken with and participated in conferences with Chase and Gary and Brian in the past. You're in for a real treat and hopefully a lot of good information sharing. My presentation is going to focus primarily on air quality impacts. We're going to touch on air dispersion modeling issues. Sorry, I didn't mean to advance that slide. Air dispersion modeling issues, a little bit of emissions testing, and then do my best Carnac imitation with where we're headed with the state of regulations. So here's the overview. Probably the first half of the discussion would be talking about air dispersion modeling and some of the issues, some of the technical issues that come up when we attempt to do that. We'll talk about that future state of air quality regulation and some key takeaways. So on the technical issues side, in order to be able to model, you obviously have to have information about the source, the facility, stack heights, things like that. And it really starts with the emissions profile, which pollutants you're modeling, PFAS being a list of 10, 12,000 different compounds with very different physiochemical properties. A lot of detailed information is needed from each and every stack in order to construct a model that represents or attempts to simulate the real world application. And we're going to talk about some of those technical issues. There are many more beyond those that I list, but some of the more critical ones in my opinion. And so we start with the actual phase of the emissions. Chase will be talking about, and Chuck too, some gas phase versus particle phase PFAS. They are present in both forms depending on the compound specific. Of course, the size of the particulate, big heavy particulate tend to settle out more quickly than volatile fractions, which can go long distances, as we'll state. And so particle size is a very important element when plugging it into a dispersion model. We have a multitude of models that we can choose from. I'm going to share with you some relatively recent research and some older research, and then compare and contrast that with an actual case study. And we'll see some similarities and some of the departures between the various models. And then finally, when these pollutants get into the atmosphere, if it's a dry day, normal atmospheric conditions will dictate, but rain or precip can cause these water, especially the water-soluble PFAS compounds, to fall out in locations other than where momentum or buoyancy would otherwise take them. So that's an important consideration too. So in order to be able to quantify emissions from an industrial source, for instance, USEPA Advanced OTM, Other Test Method 45. This is the current state of the science relative to quantifying PFAS compounds, or at least 50 thereof, from industrial and other types of sources. The schematic on the right is the train, and I'm going to click on, or put my laser pointer on here to show you a couple of things. So this orange shaded area is the front half rinse. The filter is part of that, and so that's a sample. The back half rinse, this blue area, is a second sample. An XAD resin trap, which absorbs certain polar compounds, is a third analysis. And then these impingers with specific chemistry in each impinger, which I won't go to in detail, is another sample. And then finally, a breakthrough XAD resin trap. So that's the current test method that's set up for quantifying roughly 50 different PFAS compounds. you'll note that for those of you that are air people, this is predicated. It's a modified method 5. Method 5 is the US EPA standard reference method for quantifying particulate matter. And so it's predicated on a particulate collection system, this sample train being the system. And so for those reasons, this method, OTM45, is generally capable of quantifying particulate phase emissions. And this is important. This is an important distinction to make. Many legacy PFAS compounds, the PFOA, PFOS, PFNA, etc., they behave in the atmosphere as particulate matter, not as gases. And because of that character, they behave differently than, say, benzene or toluene in a vapor phase. So it's an important distinction to make, and OTM45 makes that distinction by collecting them and quantifying them as particulate matter. A quick disclaimer, OTM45 did not go through the formal rulemaking process. EPA advanced this method because it knew that there was a need for quantifying PFAS from industrial sources. I'm saying industrial, but it's not limited to that. And this was their first attempt, right? And so as we learn more about PFAS, as our analytical methods, as Chuck will explain, as they advance, adaptive changes will be made to OTM45, I'm certain of it, before going through, formal rulemaking. So right now, this is the state of the science. It doesn't mean that it's the end-all be-all. It's our first attempt. So I mentioned very specifically that, that is used to quantify particulate-based PFAS compounds. We obviously need, because we know some PFAS are volatile, and so methods are in the work. EPA is developing additional test methods, specifically OTM50 and OTM55, to quantify different types of volatiles. So OTM50 is based on a SUMA canister train, very similar to ambient air vapor intrusion investigations, for instance, with a leading impinger solution in front. This is to capture non-polar but volatile PFAS. And perhaps most importantly, it's going to include guidance for TICs, tentatively identified compounds. As we'll talk later, when PFAS go into the environmental media, whether they're in a solid waste or something like that, it's possible that PFAS are combusted in sewage sludge incinerators, in municipal waste incinerators. And there's a growing need to be able to quantify tentatively identified compounds resulting from maybe the partial oxidation or partial incineration of other PFAS or fluorinated materials for that matter. So OTM50 is a step in that direction. Similarly, OTM55 will capture non-polar semi-falls. And this photo down here in the right-hand side is, again, a modified method 5 train that will build on the SW846 method 0010 for quantifying semi-falls. So these methods are in development. They haven't, been officially approved yet. Still additional research being done by Stephen Jackson and others, Jeff Ryan at ORD. So expect to see some of that come out in the next, probably later this year or first part of 2024. Switching gears a little bit, I want to talk about, now that we know how to quantify or believe we know how to quantify PFAS emissions from point sources, what do we need to do to be able to model them besides, just the emission rate information? And I'm going to point you in the direction of two papers, one by Emma D'Ambro and Ben Murphy at USEPA. It was published at the beginning of 2021, where they modeled the emissions from the Chemours Fayetteville, North Carolina facility using emissions data that Chemours had provided to North Carolina DEQ. And so what they did was they plugged the physical parameters and the emission rates that Chemours had given them into a dispersion model, the CMAQ model. And then they compared the results of that model to rainwater samples that North Carolina DEQ had collected, around the facility to study that wet deposition and dry deposition of the PFAS compounds being emitted from Chemours. They modeled all of the PFAS, though, as a gas-based compound. It's the first thing I want to point out to you, presumably because they didn't have particle size data. So it's important to recognize that that is a distinction when we get to the case study, differences that you need to be aware of as a model. So their key findings is that CMAQ did capture the spatial variability extremely well. Predicted concentrations, though, were only half of those observed in the field. And they pointed to meteorology differences. Maybe the emissions were slightly different. The chemical properties of these individual PFAS diffusivities, densities, very important inputs to a dispersion model. And then sample collection methods may have been another source of error. So their conclusions, though, and this is the key takeaway, the second bullet, you see that only 5% of all of the PFAS that Chemours emitted and 2.5% of the Gen X, which was the dominant PFAS compound emitted by Chemours, only 5 and 2.5% are deposited within 150 kilometers of the facility. And that's not unexpected, right? Because they modeled it as a gas. Gases go a long way, unlike particulate, which tend to deposit, closer to the facility. They also found that compounds with acid, so the PFOAs, for instance, carboxylic acids, have higher deposition due to that water solubility and pH partition. So a very first of its kind evaluation of a model, good agreement, relatively speaking, at least order of magnitude. But Emma and Ben indicated that even more research is needed into how to model PFAS accurately. That's one key takeaway I want you to recall when we get to the conclusions. Back in 2010, Catherine Barton from USEPA and others published a pretty simple paper, but they studied PFO emissions, the salts and whatnot of PFOA from the then DuPont, now Chemours, Washington Works site in outside of Parkersburg, West Virginia. And instead, they used AirMod, which many of you probably know is the standard regulatory model that we use to model emissions for regulatory applications, whether it's PSD permitting, what have you. And then they compared that to measured environmental data, specifically ambient air samples, soil and grass samples that were collected in the neighborhood. It's the Washington Works site. They too modeled PFO as a gas-based compound, another very consistent with the D'Ambro and Murphy investigation that I just talked about. Catherine Barton and others concluded that AirMod was accurate in identifying the maximum air concentrations, so spatial variability, and soil and grass impacts. They attributed the departure, which wasn't as significant as Emma and Ben found, to meteorological input uncertainty and some conservatism in the prime algorithm evaluating building damage. That's a detail of the model that I'm not going to go into. But what perhaps most importantly, they found that dry deposition was far more impactful than wet deposition particularly with increasing distance from the source. I want you to follow that one away too. So now I'm going to turn my attention to a current case study, if you will, where we have modeled a PFAS industrial source, and I'll share those results with you, and we can compare and contrast, what our results showed versus what those two prior investigations revealed. So, had a client site in northern New England, small industrial manufacturing operation on a 13-acre property, multiple private public water supplies in the immediate area, prevailing winds out of the southwest, and you can see the windrows up here for that site. So pretty typical, nothing too over the top relative to the local area. The facility itself, as I said, is a rather small manufacturing shop, less than 50,000 square feet. For its 40 plus years of existence, it's operated the same processes, albeit with different chemistry. It's a surface coating operation. They coat wires pretty much with manual and robotic operations. Some of those coatings contain PFAS chemistry, and they're applied with, as I said, robotics, conventional spray guns or manual spray guns. They have a filter, sort of like a paint spray booth with a wall of filters, very traditional. No other form of control at the time. Very similar. So it's a normal surface coating operation. Paired with the spray booths, they also have curing ovens. So the curing ovens coat the coatings using infrared or convection type drying. So we have the potential for PFAS in the coatings to be emitted from both the spray systems as well as the cure ovens themselves. And so we did a rather elaborate source testing investigation of spray booths and bake ovens. And these are the inherent results. So if you'll recall the stack test method, we talked about the front half composite. That is the filter and the front half rinse, okay? And so for PFOA, which is all that this chart is attempting to show, about 3/4 of the total load of PFOA ended up on what we call that front half. So either on the filter or in the rinse of the probe, or the probe, the nozzle connected to the filter housing. What that tells us is the filter, just so you know, has according to OTM 45, has a 0.45 micron filter. So essentially anything that gets by that filter is by definition submicron. So a lot of the PFOA is in a filterable fraction, at least 3/4 of it. The rest coming out in either the back half or which is the XAD resin, or the water impingers, the liquid impingers. And so this is important because now we know, at least for this site, from the paint spray booths, 3/4 of it behaves as particulate. It really all behaves as particulate, but it's rocks, relatively larger particulate that is capable of settling out. In the bake ovens, a similar fraction was found. So about 2/3 of the particulate was collected from the bake ovens for PFOA, manifested itself on the front half of the samples. And as I said, it's important. I didn't show, or don't have a similar graph here, but for sulfonated compounds, none of them were filterable. Everything was submicron. That's an important thing to recognize. And I have about 5 or 6 minutes left, I think, so I'm going to go through the rest pretty quickly. We're on good shape here timing-wise. From a particle size diffraction or distribution point of view, you can see here that we have some very small particulate. This would have been stuff on the filter. These these three here. This might have been in the back half. So a lot of it is filterable, and that's important when looking at abilities to reduce those emissions. If you were to try to put in another HEPA filter or something like that, you would be able to reduce about 75% of the particulate because it was a filterable fraction off the spray booth and 2/3 of it from the bake oven. So very important, the size of these particulates. These go as inputs into the model. And, lighter particulate are going to travel longer distances. That's another distinction to make. So here's the model results very quickly. We focused on depositional rates here in grams per square meter per year. Not surprisingly, deposition rates fall off the farther you go away from the facility. But what I'm going to highlight for you to compare to those other two papers is on a mass basis, 80% of the PFAS from this facility goes beyond the 10-kilometer grid that we simulated. We simulated for regulatory purposes a 10 by 10 kilometer grid. And you'll recall that the other papers indicated, the D'Ambro paper, 92.5% or something went beyond 150 kilometers. So these PFAS go a long, long way. And it underscores why the air pathway, and we're not even talking about background concentrations in the atmosphere, are going to play a key role as we move forward with air regulations and evaluating the implications of air emissions of PFAS compounds. So turning quickly to the current state of regulation. I always refer to air quality as an airhead. All jokes aside, air is the redheaded stepchild of environmental regulation. When we look back at the 70s and 80s, we had the Clean Water Act, we had RCRA and CERCLA and Superfund. All of those things got deserved attention. And then in 1990, we got the Clean Air Act amendments of 1990, which is really the most significant and most recent piece of major legislation, air, water, waste. So air is largely going to take a back seat to many of the other media, and that's okay. And that's taking shape here as we talk about proposed MCLs and cleanup levels. We have only begun to scratch the surface, right, of air quality regulations. So some states are taking it upon themselves. What are they doing specifically? Well, they're targeting facilities that may use PFAS chemistry, and they're using the permitting function as a way to reduce or control those emissions. These are air quality thresholds, guideline values, whatever you want to call them, in various states. And I only provided this slide to show you that it's starting. More states have numbers now than when I prepared this slide originally. The values are also being refined. And so that's another thing to keep in mind. I think you'll see more of that as we go forward. We have 2 years of toxic release inventory data from affected facilities. And this is just a capsule summary. So you see 38 facilities that reported in 2020 and 44 in 2021. EPA was stunned that it wasn't in the thousands. They've identified as many as 30,000 facilities in this country that are known or suspected of using PFAS. And their research has indicated unequivocally that the reason the vast majority of facilities have not reported is due to this de minimis exemption. The de minimis exemption essentially says for carcinogenic compounds, it has to be present greater than 0.1% by weight in the material, or 1% for non-carcinogenic compounds. And PFAS in general, when used in materials, they're used in very generally speaking, very dilute concentrations. And the vast majority of facilities admitted to EPA that they are used in concentrations below de minimis and therefore did not require reporting. Therefore, EPA has proposed, not acted upon it yet, to remove that de minimis exemption. And it's important, it's incredibly important that they do, if you ask me, because we don't have a true sense. So you can see here, we got 1,400 pounds of air emissions from these 44 facilities. What if you were to scale that up to the, let's call it 20,000 facilities that may actually use PFAS compounds? This number is going to jump. It may not jump proportionately, but it's a lot more than 1,400 pounds. And when we talk about exposure levels in the part per trillion range, pounds matter, okay? So air emissions are not negligible, and I'm hoping that EPA does remove the de minimis exemption. I think they're inclined to. They are seeking public comment because in order to really understand the scope of the issue, we need more accurate TRI information. And that leads me to the future prospects of PFAS air quality regulations. So additional TRI reporting will help inform industry contributions. Is it an important pathway? I say yes for a variety of reasons. They have already started, this is USEPA that is, issuing information collection requests, ICR requests to affected facilities, seeking basic information about not only the use of PFAS, but potential air emissions from plating operations, semiconductor, chemical manufacturing, surface coating, and the like. You'll see a continued evolution of state regulations, as I alluded to, New York, Texas, Minnesota, and others jumping on with attempts to regulate emissions from existing facilities. Eventually, you're going to see some PFAS potentially designated as hazardous air pollutants under the Clean Air Act, and then the potential exists for national emissions, NESHAPs, hazardous emission standards for hazardous air pollutants being issued for select source categories. It may only single out the largest sources, and I identify MAT, which is applicable to major sources, and GACT, which is applicable to area sources. The vast majority of facilities may not be emit 10 tons a year. So I suspect the majority of NESHAPs that will be issued will in fact be GACT standards applicable to area sources rather than 20,000 pounds a year of PFAS emissions. So that's the future that I see. Quite frankly, as I have on the next slide, key takeaways, we're probably talking 5 to 10 years at best before that happens. It's a long time in coming. It takes an eternity for us to gather the information, and that's why that TRI data is important. So without further ado, I'm going to talk about these additional test methods are on their way to help us quantify emissions. Various dispersion models are available to predict PFAS impacts adjacent to a facility, but it's critical from a fate and transport perspective to understand the phase of those emissions, whether it's particulate, gas, or both. Additional TRI data will take us or give us a holistic view, right, of all emissions in our communities and where they're coming from and in the magnitude of those emissions. In the interim, just as we're seeing on the state level for groundwater and soil and biosolid standards, you're going to see individual state actions regulating PFAS air emissions. And then finally, actual adoption of NESHAP standards will bring up the rear, again, 5 to 10 years, but may only target the largest of sources. So Jaana, I'll turn it back to you. Thank you very much.
Thank you, Matt. Liz, do we have a bit of time to address a couple of questions?
Yeah, I think we do. We'll just take a couple. I have a couple here that I've written down. First one has to do with the analytical methods. Is it anticipated that thermal desorption will also be included in the OTM 50 method as an alternative collection media? I think alternative to the canister. Do you know if that's being considered?
It is being considered. I can't say that it's likely, or the SUMA can for OTM 50 is right now what EPA is hanging the hat on, but I wouldn't rule it out. I don't think there's anything wrong with thermal desorption.
Right. Okay. This question, I think it was in reference to the modeling slide on the Comores site. I think your first modeling example. The question is the meaning of only, where you said meaning most deposition is close to the facility or most is further from the facility.
Oh, yeah, it may have been I don't want to say a typo. It's just the majority, the 92.5% of it went beyond 150 kilometers. So the model predicted deposition of Gen X and total PFAS, but only 7.5% of the mass emitted was in the 150 kilometer grid that they modeled. So it's going a long way. That's not surprising, though, as I said, because they modeled it as a gas-based emission. And what my case study attempted to do was show the effect that deposition will have when you model it as it truly behaves, which is as a particulate.
Right.
Did that answer the question, Les?
I think it did. I didn't ask the question, but
if there's a follow-up, ask me on the panel for sure.
Sure. Okay. Do we have time for one more, you think?
Sure.
Yeah, that works.
Okay. All right. So there's a question about whether this is your particular project. The question about whether the particulate filters associated with the paint spray booth may have also collected some PFOA that was not accounted for.
Sure. I mean, that's what it does do, right? And so what I didn't share in that presentation, or I didn't say it specifically, but it's true, because what we model is the tail end of a filtration system, the particulate are by definition already going to be small. And the stuff has gone through a filter. But there's leakage in filters and, holes developed, whatever. So what's important about that is the source characteristics. And so say Comores, for instance, while they're emitting, at the time prior to the thermal oxidizer, thousands of pounds a year of various PFAS compounds, including Gen X, what's really important is the phase that they're emitted in, right? And so that's what I was trying to compare and contrast.
Okay. All right. I think we have a few more, but I think we'll save them for later. And thank you very much. Excellent presentation.
Yeah, thank you, Matt. It was very informative. So our next speaker is Jace Holton, who is a senior engineer at GSI Environmental. His career has focused on subsurface vapor intrusion, indoor air quality, and soil and groundwater remediation. And Jace has authored over 20 peer-reviewed manuscripts, and he's also sitting on the editorial board of the Groundwater Monitoring and Remediation Journal. And Jace's topic today is gas phase release and decomposition of PFAS under varied laboratory conditions. And with that, welcome, Jace, and the stage is yours.
Excellent, thank you. Let me just get this into presentation mode, and I think we'll be set. Okay. Well, good morning. Thank you for having me. I had to get up a little early since I sit out in Denver, but I do occasionally make it back to New England. I was born in Maine, and most of my family's in New England, so I love to get back there. So great to be involved here. So my talk today is on gas phase release and decomposition of PFAS under varied laboratory conditions. And I'm going to go into a little bit of background before I jump right into our research, just covering a tiny bit on PFAS and air and some of the initial research we did starting in 2018, since it'll help me kind of tee up some of the research that we're currently working on. I'll then get into our National Science Foundation project, which is gas phase PFAS and organofluorine release from AFFF, and getting into the projects that we have recently wrapped up, which involves development of Henry's Law constants and a paper that was just released on gas phase decomposition. And so I'll then wrap things up and be sure to leave some time for questions. So to get started, we'll just go into some high-level background. I won't spend too much time here, but again, I think it kind of just helps me tee up the problem. So starting at the global scale, I'm just going to highlight a study out of Canada that was released earlier this year in February. They evaluated the distribution of select PFAS at 41 sites, including polar sites, urban or city, heavily populated sites, and rural and background sites. And they found long-chain PFAS, such as C9 to C21 perfluoroalkyl carboxylic acids, or PFCAs, at every site evaluated. Now, given the thousands of pounds that are being released from some key contributors here in the U.S., maybe that's not a huge surprise, as Matt just shared with us. But I wanted to go over some of the trends that they saw. Now, the study authors also evaluated the temporal trends of these PFAS. They have data going back to 2009. They almost have about 9 years of data, 2009 to 2017. And so from a subset of sites just in the northern hemisphere, they looked at these temporal trends. And what they found were that several ionizable PFAS were increasing over time. So PFOS, PFHXS, and PFNA were all increasing over time. Conversely, they found that neutral PFAS, or what we sometimes kind of like to call volatile PFAS, were either stable or declining. So things like the fluorotelmer alcohols were either stable or declining. I'll point out that concentrations here are in low, on the high end, are kind of in the low nanogram per cubic meter range, and they're also it's airborne PFAS, so we're talking about gas phase and particulate bound PFAS. But just to give you an idea of what kind of concentrations we're dealing with, think low nanogram per cubic meter range. This study utilized sorbent impregnated polyurethane foam discs. They're passive air samplers. So again, both the gas phase and particle bound phase are going to be included in the results. As Matt discussed, that's most likely going to be dominated by the particle phase. But the key point here is that airborne PFAS are globally distributed, and they're commonly found or ubiquitous in ambient air. Okay, so moving to indoor air, that's kind of my bread and butter. Fluorotelmer alcohols, let's focus on those. Now, a 2021 study out of University of Rhode Island found that fluorotelmer alcohols are nearly ubiquitous in indoor air. The study utilized a passive sampling technique to sample indoor air of numerous kindergarten classrooms, university classrooms. Of course, they tested the residences of the graduate students working on it. They also tested a carpet store and some outdoor recreational stores. And lo and behold, they found fluorotelmer alcohols everywhere they looked. And for example, concentrations in the kindergarten classroom ranged up to 500 nanograms per cubic meter for 8,2 fluorotelmer alcohol. Now, the highest indoor air concentrations of these fluorotelmer alcohols that I've seen reported are in occupational settings. So there's a good example from ski tuners. There's been a couple papers on this, but in an initial study on ski tuners, they found 19 perfluorinated carboxylic acids, so PFCAs and sulfonates, present in the blood of 13 professional ski tuners at elevated concentrations. The room air in which the employees worked contained about 800 up to, so at the low end, 800 nanograms per cubic meter up to 250,000 nanograms per cubic meter for 8,2-fluorotelmer alcohol. So this study has been followed up with a couple others focused on ski tuners, but it's raised concerns regarding the potential impact of these neutral or volatile PFAS on human health, particularly in occupational settings when there's potentially quite high concentrations. Now, when that study was initially published, the hypothesis was these high concentrations are leading to these high concentrations of the PFCAs in blood. Now, that's not a bad hypothesis, but there's some, I guess the thought was that it was all through inhalation. However, there's some recent research that just came out in late March, which says that the dermal exposure pathway for these neutral PFAS might actually be more significant than inhalation. But I will warn you that I am an engineer. I'm not a risk assessor, so that is, that's not mine to determine. So I encourage you to read this new paper it's out of University of Oregon and University of Washington, John Kissel. It's in Environmental Science and Technology, but it basically argues that this dermal exposure pathway may be fairly significant for volatile PFAS. So that gives us a little bit of background. Now, here's kind of where I come into the picture. My background is mainly in vapor intrusion. My graduate research was kind of a long vapor intrusion study, and I've been, usually when I present at conferences and webinars, I'm talking about vapor intrusion, but starting in 2018, I started diving into this PFAS subject because so many people were talking about AFFF, and I wanted to know, well, are there any PFAS released to air during that application of AFFF, or when that AFFF gets heated up when putting out a fire? And when I asked around about this, I got a resounding no. However, I was able to convince a colleague of mine when I was working at CH2M Hill, actually it was Jacobs by then, but a colleague and I, we convinced Jacobs to give us $5,000 to look into this, just very high level research. So this led us to this initial study. Now, before I get into that study, basically what we did was we took AFFF, we shook it up, and we measured the headspace. Now, let me get into kind of how we did that and some of the complications that resulted. But I'll first just get into what we used for the analysis. At the time, we had seen a lot of these X80 polyurethane foam samplers being used in the literature for ambient air monitoring. So, and we found an analytical lab in California that was willing to run some AFFF headspace samples for us. So the first method we used was this X80 puff sampler. The thing I want you to note is that this is analyzed by liquid chromatography, LC-MS, which differs from the second method we use. The second method is kind of like a modified USEPA method TO17. It's a thermal desorption tube that is used to collect the headspace sample. That sample is then, that thermal desorption tube is sent to a lab, thermally desorbed, and then analyzed by gas chromatography, mass spectrometry. So what I want you to take away from here is, okay, so we have two methods, one analyzed by LC-MS, one analyzed by GC-MS. And that second method has that thermal desorption extraction component. So, okay, so this gives you a little bit of an idea of the experiment that we ran. This is very, very simple. So we filled a 20-liter container. And let me back up. This was done with a colleague of mine at University of Nevada, Reno. We had his graduate students fill 20-liter containers with a mixture of AFFF and deionized water. The AFFF was agitated before we turned on an air pump to collect samples within the headspace. We then monitored temperature, relative humidity, and air flow rate. And so this experimental schematic that I have shown on the slide here is for the thermal desorption tube chamber setup. So very similar, comparable setup used for the X80 puff samplers, but this kind of just shows you kind of how we ran this experiment. The PFAS that we used was derived, or the PFAS in the AFFF used was derived from fluorotelmerization rather than electrochemical fluorination. And fun fact, we purchased the AFFF on Amazon Prime, which they actually, it was Prime delivery, 2 days, got the AFFF to University of Nevada, Reno. I checked this morning to see if you could still do that. You can't, which is probably a good thing. But that's how we did this, got this initial research started. And let's get into the results. So this plot shows PFAS results in micrograms per cubic meter on the left-hand y-axis. And you'll notice I have a secondary y-axis just for PFOA, and I'll get to that in a moment. But I'll first just point out that 16 PFAS were detected in the headspace of the agitated AFFF, but it was unclear why we were seeing these carboxylic acids like PFOA. And so since this research has been published, there has been one other group that has found the same thing, and they found PFOA in air after the application of AFFF. However, some chemists at Oregon State University have found conflicting results, and they believe it could be an analytical issue. Now, what you'll note is that the most abundant PFAS detected in the headspace was PFOA at over 10,000 micrograms per cubic meter. But I'd like you to note that it was only detected by GCMS. And as I mentioned, we got some comments on this paper from Oregon State University, and they thought maybe that we weren't seeing PFOA, and actually we might be either seeing PFHP or that we might be generating PFOA through thermolysis, either during the thermal desorption process or at the GC inlet. So this kind of small project turned into something a bit greater. We turned around, took these results, since they were a bit confusing, and went to the National Science Foundation and proposed this project on gas phase and organofluorine release from AFFF. Now, this is a grant opportunities for academic liaison with industry project. So it's essentially that means that I take on some mentoring and some teaching responsibilities. But really no money is exchanged between industry and NSF. This all the money goes to University of Nevada, Reno. So for me, this is more of a passion project, and I'm lucky that my company kind of lets me do these things. So we started this project in July of 2021. Dr. David Hannigan at University of Nevada, Reno is the principal investigator. I serve as the co-PI. Ibrahim Abu Salat was our first student on this. He's now at Fraunhofer. Junli Wang is now a postdoc at UC Riverside. He was also a student on this. And now Seth McCoy is our current PhD student working on this at University of Nevada, Reno. So the first step for this project was development of Henry's Law constants. That was one thing that we, in kind of diving into this arena of volatile PFAS, realized that there was a lack of chemical properties data relevant to volatilization. And so we didn't develop this. We looked at the literature to find different ways to develop Henry's Law constants and identified this approach that's fairly robust. So here's just another schematic. This one's showing the method for preparing and analyzing the headspace samples. Now, we're doing this again by GCM-SMS, but there's no thermal desorption step, so which we think is one of the analytical issues we're having, which we can get into later. So we use GCM-SMS for determination of those of Henry's law constants. Now this approach is quite comparable to one developed by Robbins, Wang, and Stewart in 1993, and it's been validated by several others for developing dimensionless Henry's law constants for low concentration contaminants in environmental matrices. The method involves regressing the reciprocal peak areas produced by sample headspace injection into a GC against varying sample headspace to water volume ratios. So just briefly, in dilute solutions, partitioning to the gas phase to achieve equilibrium is going to cause a corresponding decrease in the aqueous phase concentration. So the equilibrium gas phase concentration is going to be dependent on the gas to liquid phase ratio, with greater gas ratios causing increased losses from the liquid phase and subsequently reduced equilibrium gas phase concentration. So more volatile compounds are going to be more susceptible to this phenomenon, and the result is that the slope divided by the y-intercept of the reciprocal gas phase concentration versus gas to liquid ratio regression is the dimensionless Henry's law constant. The GC peak area is directly proportional to concentration, and therefore the dimensionless Henry's law constants can be derived by just measuring the gas phase peak area of an individual compound at these various phase ratios. The measurement is dependent of liquid phase concentration, given that the concentration is sufficiently low. So we aimed for concentrations well below the solubility limit. So the key point here is that the method uses an established protocol for estimating these dimensionless Henry's law constants, and we kind of go through that method in our paper. But of course, the Roberts, Wang, and Stewart paper from '93 is kind of the best source if you want to look into how these were developed. Okay, so here's one representative plot used to derive the Henry's law constants for 8,2-FTOH. The solid line is the linear best fit, and the dashed lines are the 95th% confidence interval. So here the slope divided by the y-intercept is what gives you your dimensionless Henry's law constant. I've added a shortened version of table 1 from the paper, which shows a few of the Henry's law constants we've calculated to date, as well as the values used for those calculations. Okay, so, oh, sorry, I went backwards. We also examined the impact of the water matrix on volatility. So we aim to look at environmentally relevant matrices. So we included 2 tertiary wastewater treatment plant effluents, tap water, and groundwater from a treatment zone monitoring well near an active U.S. Air Force base. And in all cases, no PFAS was detected in the headspace before they were spiked with PFAS. Now we spiked them either with 4,2-FTOH or NET both. And the Henry's law constants that we measured for these different water samples were not statistically different in the varying water matrices when compared to the original deionized water. And thus the interactions between PFAS and constituents present in these typical environmental samples had no significant effect on the volatility. Therefore, it is expected that the reported values are applicable to a wide range of environmental matrices, again, given that concentrations are reasonably low, or below the solubility limit. It's probably a good benchmark. Okay, in the interest of time, I'm going to skip over vapor intrusion potential because my colleague Brian Schumacher is going to get into that, but I'll just note that the Henry's law constants that we developed do meet EPA's vapor-forming chemical criteria. However, I'll also note that those same compounds don't have sufficient inhalation toxicity data to develop risk-based screening levels yet. So I'll leave it at that and give, you can save your hard questions for Brian. Okay, so one more thing on gas phase decomposition. Now, gas phase decomposition, this is another aspect of our NSF project. We know that it's been of great interest to those working on thermal treatment. Now, it was of interest to us because of the application of AFFF on fires. But now, thermal treatment is likely kind of a bigger research area. So we kind of focused a little bit more on that area in writing our paper. But for those that are interested in incineration or smoldering or even the regeneration of granular activated carbon, gas phase decomposition is something that we really need to pay attention to. There's a substantial body of research focused on computational predictions of the decomposition of PFCAs. That's going to be based on density functional theory. However, experimental results that have been put out, although limited, haven't always agreed with the computational predictions. For example, typically, studies suggest that the primary pyrolysis mechanism for PFCAs is the first reaction shown on the right. That's going to occur through HF elimination, with the other two reactions 2 and 3, proposed as more minor pathways. However, when they've looked at PFOA decomposition experimentally, they found that they only saw reactions 2 and 3. So there's kind of a bit of confusion. These computational predictions don't really take into account all the necessary variables. So that's where our research comes in. But furthermore, current experimental research is primarily focused on the temperature required to decompose PFCAs rather than the mechanism. So anyways, that provides you a little bit of background of why we wanted to look into gas phase decomposition. One last method schematic for you. We packed a quartz combustion tube with quartz wool or platinum foil and used that for testing the potential for catalytic degradation. And we ran oxygen or nitrogen carrier gas pulled through the combustion tube at 300 mils per minute. In the center of the schematic, a stoppered vial containing either perfluoropropionic acid or perfluorobutyric acid was connected in parallel with the carrier gas. And then the combustion tube was connected to a Fourier transform infrared spectroscopy cell. So we selected those two compounds, PFPRA and PFBA, because they were volatile enough in initial experiments to produce an FTIR signal. But using this setup, we evaluated 4 variable conditions. We looked at 2 different reactants, so our PFPRA or PFBA, and we looked at temperatures ranging from 200 to 780 degrees Celsius. We looked at 2 different atmospheres for either pyrolysis or combustion, and then we looked at the different packing materials, either quartz wool or platinum wire or platinum foil. So just for the sake of time, I swear this is my last slide before summarizing. I'll just go over the results for PFBA, which are summarized in this picture on the right. The picture shows the dominant products across the temperature range tested for both carrier gases and the catalyst used. So this complicated CF3 compound intermediate, that was the dominant product of pyrolysis produced by HF elimination. Now for combustion, carbonyl fluoride or COF2 was the primary product at temperatures below 400 degrees. And as the temperature of the furnace got hotter, silicon tetrafluoride became the dominant reaction regardless of the catalyst used due to reaction with the quartz combustion tube itself. Because we used quartz wool, but the combustion tube was made of quartz. So that's why we think we were producing silicon tetrafluoride even for when using platinum as a catalyst. So the catalyst used here did improve decomposition efficiencies. The addition of platinum wire or foil as a catalyst improved the combustion of PFBA to carbonyl fluoride at temperatures as low as 200 degrees C. And quartz promoted, like I said, the combustion of PFBA into silicon tetrafluoride at higher temperatures. Both of these results highlight the importance of surface reactions, which are not typically incorporated in those computational predictions I mentioned before. So just to quickly summarize, and I'm sorry this went a little longer than I had planned, we measured neutral PFAS in the headspace above concentrated AFFF. Since we've done that experimental work. Folks at University of Oregon have measured fluorotelmer alcohols as high as the milligram per liter range in select select AFFF. So these compounds are present at relatively high concentrations. Henry's law constants were also developed for 15 PFAS, and all the values we calculated meet the vapor-forming chemical criteria used by current vapor intrusion guidance, both state level and federal. And finally, decomposition mechanisms for PFPRA and PFBA were evaluated, and they highlight the differences in computational experimental results and the importance of surface reactions. So I'm sorry if I had to rush through that a bit, but I appreciate you listening, and would be happy to take any questions if we're allowed to go into the break.
Thank you, Chase. I think we'll leave the questions to the panel at the end, and I'll turn this over to Jessamine.
Right, so we are going to take a quick 5-minute break. We'll give you the full 5 minutes, and then when we're back, we will resume with our next presentation, who is Gary Hunt. So for now, you have 5 minutes to go wander, grab a cup of water, get a refresh on the coffee, and we'll see you momentarily. Thanks all. Get started again. Welcome back, everyone. This is a little bit like musical chairs when the music stops. Hopefully everyone could hear the music. We will get the program started again. So I will turn things back over to Jaana to introduce our next presenter.
Thank you, Jessamine. Our next speaker is Gary Hunt, and Gary is the Vice President and Technical Director at TRC. He's also an internationally recognized expert on persistent organic pollutants and other emerging contaminants. He is a subject matter expert on PFAS in the atmosphere, including measurement, distribution, occurrence, and transport and fate, and has authored more than 125 journal manuscripts and symposia presentations. And today, Gary's topic is PFAS monitoring in air. And thank you for joining us, Gary, and the stage is yours.
Thank you, Jaana, for the introduction. Can everyone hear me? Okay. This morning, we're going to talk about monitoring of PFAS and ambient air. We've heard some of that already from the prior speakers. And I'm going to talk about methodology. I'm also going to look at some data, our data, as well as others, and also behavior of PFAS and ambient air. That topic was touched upon earlier, but I'm going to explore it a little deeper. Next slide. Regarding ambient air monitoring methodology, reference was made to passive sampling techniques such as using polyurethane foam or puff and sorbent-impregnated puff. XAD4 is one example. And then there's active sampling techniques, high volume and low volume, using XAD sorbent, such as with EPA method TO13A, which is a methodology for PAHs in ambient air, and then a sandwich or a combination of puff and XAD for a collection of a variety of semi-volatile organics. Next slide. What we're going to talk about here is TRC embarked on a methodology development or validation, I should say, program in conjunction with Eurofins Test America to come up with a methodology that we could use for collection of PFAS, a variety of PFAS in ambient air. The reason being there's really an absence of the standard method or a TO method or a federal reference method at the present time. So we participated in a jointly sponsored and self-funded program. Initially, there was a pilot study that was using existing EPA sampling and analysis procedures that were adapted to PFAS measurements in ambient air. And then lastly, we wanted to apply a methodology for measurement of PFAS existing in a number of locations in the continental U.S., and I'll be showing you some of that data as well. Next slide. Here's the target list that Eurofins use. There's about 32 compounds here. I won't go into them because, as you all know, the chemistry of PFAS is very complicated. And I'm a chemist, and I can tell you it's the most complicated class of compounds that we've ever really encountered in the environment. These are our target analyte list. Next slide. As I said, we selected the high volume ambient air sampling technique, EPA method TO13A. I'm very familiar with this method. It's used for PAHs and other semi-volatiles, and I'm happy to say that I'm actually referenced in the method at the end for some work we did with PAHs back in the 80s. Design considerations for the method: there was going to be a glass fiber filter or quartz filter for collecting particulate. We looked at a number of solids, sorbents, puff, XAD for vapor phase, gas phase. Filters and sorbents were pre-cleaned and proofed in the lab. There were field trip blanks, method blanks. It's important to assess artifacts in the media, as well as contaminants potentially introduced or sample handling in the field. And then the adaptation of the method was to use isotopically labeled PFAS as field surrogates, both spiked in the trap set before they went out into the field, as well as back in the lab to assess recovery of the native compounds. And this essentially would quantify the accuracy of the combined sampling and analysis procedure. One thing I want to point out, and I'll go over it a number of times during this presentation, is contamination from PFAS is a very important thing to address. It's going to be there. If you don't see it, you're doing something wrong. Your key or your main objective is to reduce the level of contamination so that you can get a reliable measurement on the native compounds in ambient air. Next slide. We adapted a number of other quality control measures. Co-located samples were used in all cases. We didn't take just one sample. There were two, some cases more. Redundancy as an insurance policy in the event that the field event is aborted or the data from one sample is invalid. And it provides precision of the combined sample collection and analysis procedure. Our analysis was done by isotope dilution, LCMS, and our objectives were to get detection limits that were matrix dependent, compound specific, and see what the influence of blanks would be on those detection limits. Next slide. We used one of the sorbents we used was a high volume air sampler sorbent module with puff XAD, as you can see in this particular photo. We got puff and XAD in this glass trap. Next slide, please. These are not samplers from our program, but I just wanted to illustrate that these samplers are used often for collecting semi-volatile organics in ambient air. On the left, there's a program that we did some years ago for the Connecticut DEP. Related to dioxins, and it was a 30-day sampling event using high-volume samplers and collecting 7,000 to 8,000 cubic meters of air. And then co-located samples out in the Gulf during the Deepwater Horizon event that occurred in 2010, and these again were co-located samples for dioxin sampling. Next slide. The first pilot study, and we did a number of them, that was conducted in December of 2019. The sampling location was near our office in Gainesville and was in Alachua, Florida, which is kind of a rural suburban setting. 24-hour and 72-hour sampling events. We used the TISH TE1000 high volume air samples. Air volumes resulting in 24 hours about close to 350 cubic meters, and then 72 hours would be almost close to 1,000, but from 935 to 974. SOPs were developed for the sampling and customized for PFAS. Each of these sampling events in the pilot were 3 co-located samples and a field blank, and each sampler had a glass fiber filter and a sorbent module in series. Next slide. This is a photo of the pilot study at Alachua, Florida, in December 2019. As you can see, the 3 co-located samplers. On the left, on the trailer hitch there, you see a meteorological tower that was used to get site-specific meteorology. We wanted to know wind speed and direction, ambient temperature, which you use to correct the air volume, and atmospheric pressure. Next slide, please. Blank results. I'm presenting these because blank results are very important. After this study, all filter blanks, including the 3 trip but 2 field blanks in the lab bank, were all clean at reporting limits of 1.5 nanograms for 30 of the 32 PFAS analyzed. The 2 exceptions shown in the bullet below observed the majority of blanks for Gen X and 6.2 FTS. All sorbent blanks, 3 trip plus 2 field and 1 lab, were clean at reporting limits of 1.5 nanograms for 25 of the 32 PFAS analytes. The remaining analytes range from 1 to 12 nanograms in sorbent blanks. Next slide, please. As a result of this first pilot study, we were able to achieve the detection limits shown in this slide. Absolute nanogram quantities are on the left for all of the parameters of the 32 compounds shown previously, based upon 24-hour and 72-hour, so it's a function of the air volume that was collected. And you can see the range goes from the low picogram per cubic meter range for the majority of the compounds to up to 10 to 12 picograms per cubic meter, which is again influenced by the blank contamination. We found throughout all of our measurements that the blanks dictated detection limits. You know, you might be able to get better detection limits with more volume or with analytical optimization, but the blank contamination will preclude you from getting lower. And that's true of most of these measurements. We encountered it with our dioxin program some years ago that we did for the Connecticut DEP, and we were able to achieve detection limits in the femtogram per cubic meter, believe it or not, once we got control of contamination. Next slide, please. And then we took the method out into the field and conducted field sampling events at a number of locations. And these locations were all Eurofins laboratory facilities, so it was easier to get the cooperation from the host, obviously, doing that. And they were in Pittsburgh, Pennsylvania, King of Prussia, Pennsylvania, Albany, New York, Chicago, Illinois, and Milwaukee, Wisconsin. And these were all collected in the summer, June and July of 2020. Duration in hours, approximately 48 hours. Air volumes collected and range from 513 to 659. And reporting limits, again, were a little higher than the pilot study. Again, a function of contamination and also a function of air volume. They achieved about 2.5 picograms per cubic meter. Next slide, please. Here are some of the sampling events shown on the bar graph for the blank data. And the reason I show this, and these are absolute nanograms, not concentrations, this to show what you're up against with respect to contamination. We saw in all of the field blanks that were at each of the sites were contaminated to some extent. The majority of the parameters were below the reporting limits shown, but PFBA, PFOA, and NMFOS and NMTFOS had contamination that was detected on a regular basis. The only one that was an issue was PFBA and PFOA, but when you'll see the actual data, you'll see that these levels really didn't influence the reporting concentrations. Next slide. Here's the results from the pilot study in Alachua, Florida, in December 2019, and here we can see the two compounds that showed up most predominantly, PFBA and PFPA. So that's butanoic acid and pentanoic acid. Let me see, we have concentrations of over 100 picograms per cubic meter for PFBA at all of these locations. And these are 3 co-located samples. So we're looking at those samplers that were in that prior photo. And there are 3 in each 24-hour and 72-hour segments. The mean concentrations are shown on the right. So we're well above, in most cases, or approaching 100 picograms per cubic meter. And this is not unusual. If you look at data in the open literature, there was a study done by the Minnesota Pollution Control Agency, or their regulatory agency, that showed the most predominant the most predominant PFAS compound in ambient air is PFBA. Next slide, please. Next slide, please. Okay, here are the data from the sampling events in bar graph form that I showed previously for Albany, Chicago, King of Prussia, Milwaukee, and Pittsburgh. We have PFBA and PFPEA. Again, the butanoic and pentanoic acids are the most predominant species. As you can see, we have concentrations of PFBA that are the most predominant. And the PFBA is also found at higher concentrations, and these were not affected by the blanks. As you can see, in the case of PFBA, the blank contamination in the prior slide was like 10 or 12 absolute nanograms, and that's 10 or 12,000 picograms. And when you divide it by the air volume, it's not that significant. So this is the most predominant PFAS compound in ambient air is the butanoic acid, and that's a function of its volatility, really. I don't know that it's a function of its ubiquity or a function of its unique nature as a member of the PFAS chemical group, but it's obviously one of the more volatile compounds and appears in the highest concentrations in ambient air. Next slide, please. Now I'm going to talk a little bit about passive sampling. Passive sampling is another technique. Chase mentioned it. It's been alluded to already by prior speakers. These are some sampling devices that I got courtesy of Environment Canada, Tom Harner, who does a lot of work with passive sampling. In fact, passive sampling has been used to collect most of the PFAS data internationally, particularly in Canada and Europe, where they've been looking at PFAS in the environment for a lot longer than the U.S., in fact. And here you have, in the middle of this photo, you have what looks like a flying saucer or some sort of alien device is actually the passive sampling device, and it has assorbent media in it. Next slide, please. This is a close-up of what one might look like. This is one that we used in a study that was conducted for USEPA for PCBs and indoor air. Next slide, please. Here's an interior diagram of it. As you can see, in the middle is a foam disc, in this case polyurethane foam. You can hang this device. You can position it on a bench top or what have you. And the air basically is collected by a process called passive diffusion. There's no actual pumping done, no actual flow measured, but based upon published data, or if you run co-located samples that are being collected with a pump, you can come up with a passive collection device, passive device collection efficiency or method. And as a result, you can calculate the concentration of the PFAS in ambient air at the end of the sampling event. Next slide, please. This is a description of the sampling method. It's a TISH model, TE200 PAS, two-dome design as just shown. There were polyurethane discs, 5.5 inch in diameter, a depth of 0.5 inches. Sampling rate of 0.8 cubic meters per day, and this is based upon a publication from Hazrati and Harad using the calibration of polyurethane foam disc for passive air samplers for quantitative measurement of PCBs and brominated diphenyl ethers. So you can actually use published passive collection data and to come up with an air volume, and when you have the total nanograms on the foam that's in the sampler, you can calculate a concentration. Next slide, please. And these are the samplers that we used in the study that I mentioned that was conducted for USEPA and indoor air at New York City schools, again for PCBs, but here's the same device that we would use for PFAS. And again, as I mentioned, there's no collection, no pump. You can leave them out there for as long as you'd like, for a week or a month or 24 hours or what have you. And obviously, as with the active samplers, the longer you leave it out there, the more you collect and the higher the concentrations or the higher the nanogram quantities that might be found on the disc. Next slide, please. PFAS are widespread in the ambient air globally. They're ubiquitous. These are some publications from a number of years ago showing the mean concentrations of total PFAS in air, all in picograms per cubic meter. And these are in some locations fairly remote. And I think what I'm about to say is that they're ubiquitous in the environment, as with many other semi-volatile organics or volatile organics. If you look for them, seek, and ye shall find. Next slide, please. This is a study that was referenced earlier by Matt, and this was work published by Barton et al. Back in the Journal of Air and Waste Management Association in 2006. And these data are shown here. They're adapted from Table 3 in that publication. We're showing measured concentrations only on a number of dates and no ND values. And they were comparing modeled concentrations to measured values. And the model tended to, in this study, over-predict the concentration of PFOA in ambient air outside the DuPont Washington works in West Parkersburg, Virginia. And as I said, Matt talked a little bit about this study. This is one of the modeling exercises he referenced. Next slide, please. Okay, this is a very important slide. This was from the same study, the same data set. And what they did was they looked at particle diameter. I think they had a cascade impactor. I'm not sure what device they were using. And they basically measured the amount of PFOA found on each of the different particle fractions. And as you can see here, the highest mass percent of PFOA was found on particles less than 0.28 microns. And what this illustrates is that if you get these sorts of compounds that are going to be on the particles and on the very small particles, these particles behave almost like a gas in the atmosphere, and they can travel very long distances and be deposited many, many miles downwind from the source. And this is what we're seeing with a lot of the environmental contamination situations with PFAS in the atmosphere. Next slide, please. It's important to realize that soils are a critical reservoir for PFAS because of the methodology, or the process, I should say, of atmospheric deposition. They can accumulate in the soils, infiltrate in the soils, and then over time break through or leach through the soils down into the underlying groundwater. And that we've seen this in a lot of contamination scenarios with PFAS around the country. Next slide, please. Here are some data from the Parkersburg facility. Again, this is from the Ohio State University, and this is outside the Washington Works that I just shown in the prior slides, and near Parkersburg, West Virginia. And as you can see, they measured concentrations of PFOA in groundwater. And as you can see, the concentrations up to in many cases, 10 kilometers away from, or 20 kilometers away from the source, they found measurable concentrations. The highest concentrations near the source, but as you got farther from the source, the concentration of PFOA was still in the groundwater, but at lower concentrations. Next slide, please. The state of North Carolina, and this is a study that was also referenced by Matt earlier, had a rainwater sampling program, and the purpose of this was to collect compounds, PFAS compounds, around the Chemours facility in Wilmington, North Carolina, and measure the concentrations in rainwater, which would be a good indication of what the concentrations would be getting to the soils. And these are both wet and dry deposition, obviously, since it's rain, and the rain will scrub out any particles that are suspended in the atmosphere. Next slide, please. This is GenX. They were focusing primarily on GenX in this studies around Chemours, because that was the principal compound of interest. And what this shows, this slide, is the GenX in rainwater in parts per thousand as a function of distance, parts per trillion, as a function of distance from the Chemours facility. These samples were collected in 2018. And as you can see, as you get from the facility up to a distance of 7 miles, they're still detecting measurable concentrations of GenX in the rainwater, and rather elevated concentrations, getting up as high as 810 parts per trillion. So again, this shows that the compounds, when they're emitted, because of the deposition properties, particularly if they're affiliated with particles, can travel great distances from the source. And not only travel distances, but be deposited on the soils and end up in underlying groundwater over time. Next slide, please. Again, here's another slide of the GenX in rainwater as a function of distance from Chemours. And as you can see, this is showing a gradient that goes up to 25 miles, and there's still evidence of GenX being found in the rainwater being collected by the state of North Carolina, And concentrations are smaller than the prior slide, but again, they're detected, and it shows the ability of the compound to travel great distances from the source over time. Next slide, please. Here are some data from PFAS, PFOS, in Lake Ontario, and this is old data, but I've got it here to illustrate another important feature, is that over time, the deposition into sediments and soils will increase the concentrations. And this is a slide showing the concentrations of PFOS. And as I told you, the Canadian and regulatory agencies were looking at the PFAS compounds long before the U.S. was involved. And these are sediments, bottom sediments in Lake Ontario, taken in 2006. They did dating on the soil sediments. You can actually date it using lead-210 or cesium or other radioactive elements to date the core. You section it, and then you find out the date that it represents, and then you analyze that section, and you can come up with the concentration over time. And as you can see, in this case, it's increasing from 1980 to 2006 up to 12 to 13. What are the units here? Nanograms per gram in the sediment. But the point of this slide is actually that over time, via deposition, wet and dry, particularly in this case, dry deposition, where the particles are getting to the bottom of the lake sediments, will be increased. And I would imagine that this process has continued, and these concentrations are much higher than they were in 2006. Next slide, please. So, with some closing thoughts here on PFAS, in summary, the chemistry is extremely complicated, thousands of compounds, and it keeps expanding almost daily. They have very unique physical and chemical properties. They have both what we call a hydrophilic and a hydrophobic tail, meaning that they're water-loving and water-hating, to be simplistic, and they have both those properties. Their widespread long-term use has led to their ubiquity in the environment. They're literally everywhere. And they're in air now, as we're talking about today. Air emissions to the atmosphere can contribute to soil and groundwater contamination near and distant from the source. And everybody has seen that today. Active and passive sampling methods are available. Contaminant control is critical, both in the field and in the lab. And if you work with the lab and they tell you they've never had PFAS contamination and they have it under control, then they're misrepresenting it. And EPA-sanctioned methods are needed for sampling of ambient air. A TO method, I don't know where they are in development of that, but we need a TO method for sampling, and it might include an active sampling technique like TO13A, or it might involve a passive sampling technique. And I'm not sure where I am on time, but let's see, 10:15, 10:45. I'm a little over, I guess. No, I'm not. Am I?
You're right on time. I pushed us with that break, so you're right on time.
Okay, great. Thank you. Thank you very much.
Thank you, Gary, for a great presentation. And I think that we will move on to our next speaker, who is Brian Schumacher from USEPA. Brian is the Director of Ecosystems Processes Division in Athens, Georgia, within the Center of Environmental Measurement and Modeling of the USEPA's Office of Research and Development. His current research is focused on wrapping up the examination of spatial and temporal variability in cold climate and subslab sampling techniques, and new investigations into the concept of soil gas safe communities, vapor intrusion potential of PFAS, and the development, testing, and validation of a method for vapor phase PFAS determination are currently underway. And Brian's topic today is PFAS and vapor intrusion. And with that, welcome, Brian, and the stage is yours.
Okay, I'm in the process, I hope, of getting my thing taken care of. You're starting to see it, so that's good. I'll put it in presentation mode. I hope it's going into presentation. Okay. There we go. Which screen are you seeing, Jessamine? You seeing the full screen or the presenter's
I do
one?
not see your notes, which I'm guessing is what you want.
Okay,
and I see full presentation screen.
Okay, perfect. Okay, then I'll just make sure, because I have the other one. So, okay, any which way, as long as you just see the full screen. Today, I'd like to, I gotta do the other thing. Hang on. Gotta get my laser pointer out. Okay. Today, I'm going to talk about is PFAS a concern for vapor intrusion? Your talks that you've heard so far are dealing with atmospheric air, the air that you're breathing readily, either indoors or outdoor. But in our case, we're going to take a deep dive, as Gary would say, take a deeper dive, but we're going to go below the subsurface horizon of the soil and go into the soils itself, towards the groundwater, or underneath your slab of your house, or around your basement in your house. So we're going to go in that particular manner. Let's see. Okay, what is vapor intrusion for those of you not into the vapor intrusion realm? It's basically the migration of contamination, and in this case we're looking at PFAS, from either contaminated groundwater source or contaminated soil source. The vapor phases will migrate up towards the surface. It may be impeded by a silt or a clay lens, but once it gets to the house, and here we have a slab on grade, here we have the house with a basement sitting in it, it will find its way through any cracks, crevices, sump pumps, any type of hole that's occurred in the slab of either the slab of the basement or the slab on grade. It can come through utility lines, which are basically calling them conduit pathways, so through your water line, your sewer line, your gas line, your whatever the case might be that's coming into your house. And it's affected by creating a vacuum in the subsurface underneath the slab here or in the basement. And this is done, you see in particular in winter, the stack effect, where you've got the heater going, your warm air is rising, it goes out through the roof or out through your chimney if you have a chimney, and that creates a slight vacuum in the basement or underneath the slab, and that's a driving force that pulls these vapors into your house. You can also see it on strong wind effects, and this is a case of the classic example is the airplane wing. One part of it, there's a vacuum that keeps the plane rising, and the same thing happens in the house. So there's a slight vapor, a vacuum going on here, and it will again pull the volatiles and the volatile PFAS in this case into the house. So when we're looking at it, we were asked by the Office of Land and Emergency Management, OLEM used to be OSWR for the other folks, to look at the initial potential for PFAS in vapor intrusion. Okay, and we know and you've heard that there's certain classes of PFAS chemicals that are volatile, and the question is, can they and do they migrate in the VADO zone, the soil zone, to the subslab, and eventually into the residence or the building? We started out with this class of PFAS, the fluorotelmer alcohols of various chain lengths, and looking at the folks as either it was the ethyl or the methyl. But while we're doing it, the laboratories are going to run and get these other compounds in there, PFOA, PFAS, PHEX, and so on and so forth. So we gathered all that particular data, and we're going to look at that as far as their potential for vapor intrusion. This is a pilot study, so we picked up the first shot through there, trying to make sure we have a complete vapor intrusion pathway. And so we selected a site, a PFAS manufacturer in New Jersey. We picked that because we know if there's a good chance of finding PFAS in the environment and volatile PFAS in the environment, let's go to a source. Okay, there's also, it can be done at other landfills, places where you had AFFF spills, our usage, DOD or airports, things like this, and so on. But we went to the manufacturer. So we had two basic questions that we're looking at. One is, what is the distribution of PFAS in soil gas? In the soil, which is a source, could be a source, and groundwater could be a source. And when I talk about soil gas, I'm including that in the VADO zone, as well as that which we're calling subslab gas, or the gas that's immediately below the concrete floor of your house, if it's a slab on grade, or it makes up your basement, if you have a basement type construction. And then as we continued looking at these, question came up, what phase of the volatile PFAS is occurring? Are they in a vapor phase, a pure gaseous phase? Or are they in what I'm calling here listed as a mist, and this is being associated with the soil moisture, so as a sort of a misty type of thing, so with water content in the soil? Or is it on a particulate? Is it being absorbed onto a mineral matter or onto an organic compound, organic matter that's within the soil? So here's the site. This is the Kenmore site. Chambers worked in Deepwater, New Jersey. You have the Delaware River on the side. It's a very large complex. And what I want you to focus on is this little V. You got a V right here, because we're going to zoom in on that in just a second. So we're going to take a look at the V on that road and see exactly where we're looking at and what we're dealing with. So the sampling locations, as we jump into it, here's the V that I was talking about here. Right here, this building right here with the green dot next to it is building 1156. This is the active manufacturing facility for PFAS compounds at the Chemours deep water site. So that's a source. There's also a dot there with a well that's drilled to monitor any losses at that particular site. So we also went out to 4 other areas at the particular site, which was labeled A, B, C, and D. And these are areas away from the building, so we're out of the way of the tight construction zone as well as all their operating zones going on, and found 4 areas, A, B, C, and D, that acted like or could act like a building. So, for example, A, we found that underneath this was an old building at one time. Now it's covered with gravel, so that we're looking to hope that that slab was still there in the building. B actually sits just off into this parking lot, so we have the asphalt is acting as a cap, or is acting as a slab of a building, if you will. Site C is right just outside of this building, and again, this is all paved in this area. And then Site D was outside of an old building, and that's covered with gravel. So we're hoping that those things are showing some capability, if you will, to trap the VOC, the VOC forms of the PFAS at those sites. So it's quickly flying through the sampling analysis. We did groundwater, bladder pump, unpreserved, did the standard GC mass spec, and the modified LC mass spec. The soil, we collected a composite core from surface to the depth that we could sample it to till we hit the groundwater. Again, we composited the whole core, so there weren't individual, every 6 inches or 10 inches, whatever the case might be. And we sent them off and followed the same methodology, following 8270E modified or method 537. When we collected the soil gas, you just heard Gary talk about the passive and active samplers. We did a syringe sampling for sample volumes collected of 100 milliliters, or a vacuum pump where we collected 1 liter size samples. They were collected on the multi-bed ATD tube from Camsto. So you basically connect the pipe to the source and then to the pump or syringe. You pull the gas through the tube, the sorbent captures the PFAS compounds, and then use modified TO17 for the analysis. The subslab gas is almost the same as soil gas sampling, except we put in a vapor pin that you see here. So here's your slab. You drill a hole, a pilot hole, and then a small hole. You put in there, it's got a silicone shell around it, and underneath the white cap's the nipple, so you can connect your sampling tube to this, and then use the pump or the syringe to pull 100 mils or 1 liter through there. And the end of this thing is sitting out in the space that's underneath the slab of the building or of the house. So now if we turn our attention again to what is the first question, what is the distribution of PFAS and soil gas, and that includes subslab, in the soil and in the groundwater. So looking at the data here, we're going to talk about the perfluorocarboxylic acids, the PFCAs, the ones we're most familiar with, the PBA, butanoic, hexanoic, octanoic acids. But we looked at them as when we could all the way out to octadecanoic acids. The first group here, the first 2 columns, is the subslab samples within the building 1156, that little code there. And we had 2 sites that we had the vapor pins inside the building and going through the slab. And when we pulled the analyses up, we could see the butanoic, hexanoic, and octanoic acids were in concentrations that were measurable in that vapor sample that was pulled from that particular location. And just a quick reminder, the E is that it exceeded the calibration curve as a flag. So that basically says that the hexanoic acid here in subslab sample location number 2 was at least 650 micrograms per cubic meter. So that's what we're seeing within the subslab gas as in our pilot study. If we look at the locations, you'll end up seeing the same gases are located in sample C. Location C here, that's the one that's nearest to the building 1156. And we see the same compounds, the butanoic, hexanoic, and octanoic, but we're also seeing some concentrations of the pentanoic and a little bit of heptanoic. And one of the things that's interesting to see here is the trend. Here we have the subslab, that's SS. We have it at 1 foot, and we have it at 2 foot samples with the 2 different volumes. But we see in each of the cases where we had it with the butanoic, hexanoic, and octanoic acids, we see the concentration is increasing from the subslab, or basically the surface, if you will, down to depth for all three of these compounds, down to the 2 foot depth. Sorry, I was reading the liter on that. We did see the compounds once in a rare while at some of the other locations, but nothing to be concerned with. When we look at those in the same compound list in the soil itself, this is the composite sample again of the whole core sample and pulling out the required sample volume. We basically saw everything from pentanoic all the way to octadecanoic at various levels within the A, B, C, and D locations. And C, again, is the closest to the building, and we did see the butanoic acid here. So what is interesting here is I'll see a little QA for you. The precision between the duplicates B and B are really good. So we're actually seeing real things, if you will. It's not an artifact of some other event. But we see the greatest concentrations, again, closest to the source building in location C, with them generally decreasing as you went to B's and A and D. And the green highlight here in D is just we did not pick up, for whatever reason, the decanoic to the octadecanoic in that particular sample, like we did for all the other locations A, B, and C. So we're seeing within the soil itself, there is a source, or at least an increased concentration of these various perfluoric carboxylic acids in that soil as a source term. When we look at the groundwater concentration, so now that's even deeper below, we only have locations A and D because at locations B and C we hit refusal of the drill as we're going down there. But you see for the butanoic up to the decanoic, we're seeing concentrations of these particular compounds in the groundwater itself as well. So as the question comes up, is it moving in the groundwater or is it migrating to the groundwater through the soil and various pathways and degradates? So now let's turn our attention. We're going to look at the fluorotelomere alcohols here. We got 4,2,5,2S secondary, 7,2 secondary, 6, 8, and 10,2. We're looking here at the subslab. Here's the subslab samples within the building, 1156 at the 2 locations. And we're seeing these in distinct quantities, distinct concentrations, with 6,2 and 8,2 fluorotelomere alcohol being very high concentrations within that particular location underneath the building slab. So we're underneath the concrete slab of the building. When we go look at the equivalent, the soil gas concentrations leaving the building and away from the building, same as we saw for the carboxylic acids, we see that in the subslab in 1 foot and 2 foot at the location C, the closest to the building. Again, we're seeing concentrations of all the fluorotelomere alcohols at those locations. And what's very interesting that we saw in this particular case, we just look at location C, is that for the smaller compounds, when we're up here, the deeper the sample, the greater the concentration was. But once you did the 6,2, 8,2, and the 10,2, it was pretty much the opposite. Here we have the greatest concentration was at the subslab underneath the in this particular case, underneath the parking lot. We see it here, and then we have some variations where it might be higher at the depth, so we end up high at the top, higher at the bottom, and then low within the middle horizon at 1 foot depth. So that's an interesting pattern to be looking at. We also saw that we saw some of the other compounds there as we stay closer to the building. We see some 6,2 coming up in both the A and B locations. And occasionally at the D, we did see this 5,2, but that was really at the detection limit and can't tell. I will note, and you probably observed that we had a blank concentration of the 6,2, but as far as it goes, would affect perhaps these 2 samples in the C1 foot and C2 foot, but it's clearly not going to affect the subslab concentrations at all. So we take the look at the fluorotelomere alcohols, and we're looking at the soil and groundwater. Nothing to see here, so I'm not going to go any further. They're all non-detects. So that led us to the question when we had those distributions, and we could see various compounds up in the subslab. Maybe it decreased with depth, or maybe it increased with depth. So the question was, in question 2 is, what phase are the volatile PFAS occurring? So we end up looking at and deciding to put in a filter apparatus. We used a high purity quartz microfiber filter with a pore size of 2.2 microns. And the idea would be that we'd end up trapping any particulate phase on the particular filter and then the sample go back into the thermal desorption tube. So this would be a pure gas phase, if you will. Whereas the sample here, you can see the little circle of the quartz microfiber filter would be captured on this particular thing. And then we analyzed the tube, we analyzed the filter, and we also collected a sample that was we see the sequence here is A, B, A, B, C, D. A is the unfiltered sample, B is the filter and tube sample. So we have the filter involved here. And C and D were just different size sample volumes. This was 100 mils, I believe, and this was 25 mils. So what we're trying to do with that sequence is make sure, okay, I didn't just, the difference between A and B is I drained the atmosphere. I created a new subslab atmosphere. So we repeated it, and we'll see that the A's matched pretty much and the B's matched pretty much, with an analytical error. So how did that come out? Here we have, again, we're talking with the fluorotelmer alcohols. This orange column is the original data at building 1156, and I just picked out subset, the soil gas point number 2. These are the original values that you saw before. And so what we have here is we talk about A, this is the total unfiltered tube is in green. We have the filtered tube, just the tube that passed that particular filter, here in yellow, and then the filter itself here in blue. And my clever idea, at least I had at that time, is that then therefore the blue and the yellow should equal the green. So we have that type of thing that we can look at. Let's we take a start looking at the 5,2 secondary fluorotelmer alcohol. Yes, the A and the B pretty much equal the C. Or if it made it all the way through, it's, they're not too far away. The same happens here when we're looking at the second set. This is A1, B1, this is A2, this is B2. So we're seeing the two components more or less equal, the unfiltered versus the filter and the tube behind it, and so on. But the other interesting part here is when we're looking at the smaller 5,2 secondary, we see here that we have the FTOH is in both the filter tube, so it's passing through the filter, as well as it's being trapped on the filter. Okay? So that means that would indicate here perhaps a gaseous phase, here perhaps some form of particulate phase, be it, again, a mist or groundwater that's being absorbed onto soil moisture being absorbed onto it, or it's, in some absorption onto a mineral particle or an organic particle. And we see with the rest of the compounds that were detected as we come down through here, we'll see that everything is being effectively collected and stopped by the filter, both on B1, both on B2. And even when we change the 25 mils from 100 mil sampling, it's still being caught onto the filter itself. So to summary to date where we are, we saw multiple PFAS, neutral and ionic forms. In the soil gas, we saw both the fluorotelmer alcohols and the carboxylic acids, whereas in the soil and groundwater, we're only seeing the PFCAs, the carboxylic acids. The concentrations in the soil gas phase were greatest in the subslab under the building, and then it decreased as we saw with distance going from the highest at the building, then the subslab to source location C, and then virtually nothing being present as we went further out to the locations A and D. So that led us to the question, is this the PFAS migrating as a vapor phase in the Veda zone, in the groundwater, or is it going in both? The soil data that indicated that nearly all the quantified PFCAs were found in the locations. We only saw the 10Cs, the decanoic acids in location D, and that might have been an analytical issue, not looking below those particular ones where we saw it all out to the octadecanoic size acids. There are no fluorotelmers in the soil and groundwater, regardless of the distance from the presumed source building. So that would end up saying that it's not in the groundwater and the soil yet in the gas phase, so maybe this is a vapor phase transport. The fluorotelmer alcohols are moving as a gas, if you will, a pure gas, underneath the slabs of the buildings and away from the particular site, the source building 1156. Well, it's interesting is that we end up with the carboxylic acids of PFAS, butanoic, hexanoic, and octanoic in the soil gas phase. This was unexpected because they're typically deemed to be non or very low volatility. So that led to the question of, okay, what is it? What's causing this? Is it again particulate versus gas phase, or is it something to deal with the soil gas sampling method itself? So we've gone to look at this particular aspect, and we're looking at the sampling method development phase. We have laboratory testing phase is completed, where we looked at basically instrument setup, spectra calibrations, etc. We looked at the storage stability. Yes, they're stable. They're looking at thermal. One interesting thing that come up is when they were checking out for PFOA, when you put it into the injection port or you ran your standard heat ramping programs to get the things to release from the sorbent, even without the sorbent, we're saying that in one case of PFOA, that the mass discharge ion response, we didn't see the carboxylic acid functional group missing. So that COOH group, we did not see that come out on the peak on the GC. One thing that then it does look like is perhaps perfluoro-1-heptene would be the byproduct. So it makes it a little more difficult to separate out whether it's this particular compound, the heptene, or it's truly PFOA, because again, we're missing the carboxylic acid functional group. One of the things they did do in the lab testing is they developed the flash volatilization so we can get onto ATD tubes. And then they're evaluating the filters, looking at the quartz microfiber filter again, and we're looking at a stainless steel fret. So in case perhaps the quartz fiber has some residual charge on it that could be absorbing various PFAS as it's passing through, and not really a blocking, more of an absorbing type of capacity. And we're currently doing that data evaluation. We do intend to take this even a step further and start looking at other common contaminants of sulfur, hydrogen sulfide, ammonia, and other sewer gases. So if you end up doing the conduit travel work for vapor intrusion, conduit pathways, one of those is, as I mentioned before, is the sewer lines coming in and out of your house. So we want to see whether or not the method, once it gets fit for the soil, can it handle these other various contaminants, if you want to call them that, the hydrogen sulfide, ammonia, and so on. And then we're going to do, once we get that done, off the field testing we go. And with that, I see Jessamyn's come on to give me the warning, and I'm done.
That's impressive that you saw that.
Oh yeah, well I have it on the side. I don't know why my screens do what they do, but they do.
Right, thank you, Brian. Shall we move on to Chuck?
Hey, Jaana.
Okay, great. You're in. Thank you so much, Brian. Great talk. And then last but not least, we have Chuck Naslund from Eurofins. He is the scientific officer for Eurofins Lancaster Laboratories Environment Testing and PFAS practice leader for Eurofins Environment Testing. And Chuck has worked in environmental analytical chemistry for over 38 years and is a subject matter expert in high-resolution mass spectrometry analysis and PFAS analysis. He is responsible for identifying and framing trends in analytical testing and equipment, initiates new methodology, and directs research and development. And Chuck's topic today is analytical challenges associated with PFAS in air. And with that, welcome, Chuck, and the stage is yours.
Thank you very much, Jaana, and thanks for tolerating my schedule inconveniences to you folks. So I did catch the end of Brian's talk, and that was really fascinating. A lot of good work and additional work that needs to be done. So to me it's pretty exciting about what we can look forward to. If we're hang on a second here. So if we look at and consider what are the where PFAS contamination air could be, they have a number of different sources. And as I had listed on the screen there, and why is this a problem? Why do we need to be worried about this? And some of it is because these source air emissions, we've got short and long range transport. which then potentially impacts ambient air contamination. There's some atmospheric deposition, and in fact, there have been a number of studies over the last handful of years at some specific sites that I'm not going to name, but some specific sites that have basically shown the stack emission, and from practices over the years, basically PFAS contamination and deposition as a function of the prevailing wind, right? So we've got, essentially some real life laboratory kind of evaluation to show that that's the case. And then if it's impacting and there's deposition, then we've of course got the potential for impact to surface water and groundwater and soil. Let me just change thank you. Okay, I have to change my view here for a second. So as part of the PFAS strategic roadmap, 2023, those kinds of things were identified, right? Identify the sources of air emissions, develop monitoring practices and approaches, and I think a lot of what you're seeing or hearing today is work towards that effort. I mean, we don't have, other than OTM 45, and there are some validated methods that we're going to talk about here in a few seconds, but we're still building and developing this area of analysis and this area of expertise. So we're developing those monitoring and analysis processes or approaches. That will lead into mitigation technologies, and then of course fate and transport kind of work. So, and this may have been mentioned previously, but just for point of reference, bipartisan group members introduced the Prevent Release of Toxic Emissions and Contamination Act, the proposed rule, and has a list of PFAS as HAPs, and they're looking to treat PFAS as a class of compounds. And of course, for point of reference, also states that have some ambient air criteria listed already, even in the absence of a final methodology for doing this kind of monitoring work. But New Hampshire, Texas, Michigan, New York, and Minnesota all have for different compounds, and in particular, only Michigan has something for 6.2 FTS. All the others are somewhere around PFOA, PFOS, or the ammonium salt of PFOA. So let's talk about the testing in air, and we'll just try and bump through some of these quickly, so we can get to the question and answer session where I think a lot of good information will be exchanged. And so we've got source air OTM 45, a complicated, and when we talk about the complications of the challenges with air analysis, I'm going to go into a little bit of detail on the OTM 45 here, but it's basically built around semi-volatile and particulate-bound PFAS, based off of method 0010. You'll see in the next graphic that I have for you a pretty complex and complicated sampling train. Ambient air, to date, we've basically been looking at things like a modified TO13 in several of our labs, where we're collecting samples on a puff cartridge with a puff foam along with a resin cartridge, and then of course sample preparation, extraction, and analysis using LCM-SMS, as with the OTM 45. So in both of those, because we're looking at these quote-unquote semi-volatile PFAS, or those, in most cases, anionic forms of PFAS that we've been monitoring in water and soil and consumer products also, quite frankly, we're looking for those. And so that's an extraction and analysis process that is actually quite similar to the water and soil techniques, just the sample collection is significantly different. And then vapor using a modified TO17, and there the big difference is the GCM-SMS. I'll tell you, we have done a lot of work with my colleague Heidi Hayes out of Air Toxics in California early on in their work to bring on this modified TO17, partly because we had done the fluorotelmer alcohols, and that modified TO17 using the GC triple quad technique was one that originally was sort of based around the fluorotelmer alcohols, as Brian was talking about, but then also looking at some shorter chain carboxylic acids. But because we at Lancaster had developed a technique for fluorotelmer alcohols in water and soil several years back, there were some synergies that we were able to gain between partnering together for their setup of that technique. So let's talk about PFAS and source there quickly. We've got OTM 45, performance-based method, semi-volatile and particulate bound, basically the same or similar type of compounds that we're looking for in soil and water. And look at that schematic. So if you haven't done an OTM 45 or been involved with OTM 45, that's a challenge, right? So just the sample collection is a challenge. And there are certain groups within the US that are very experienced and specialized in doing this. For us at Eurofins, we provide some of the sampling media because we like to clean and have a certifiable cleanliness of the XAD resin and components that are being used, so that'll be shipped out. But all of that sampling is done by experts in this field and area for the collection of this stack and emission gas. So you can see going through that entire and complex sampling train where we've got, because of the heat of these stack emissions, we've got condensers, we've got an ice bath for precipitating and getting condensate out of that, and backup resin tube or breakthrough resin tube, all leading to these kinds of analyses. So a sample fraction when we're looking at source air, and this is part of the reason it can be so complex for the setup, complex for the collection of that sample, but then also the analysis. So we've got a front half composite that consists of the particulate filter, the front half filter holder, probe rinses, solvent rinses of the probe. Back half is the first XAD resin tube, condensers, solvent rinses. Then there are impingers and the condensate that get extracted and analyzed. And then the breakthrough trap, which is your breakthrough XAD resin tube, which I'm just going to go back here. I thought I was going to go back here. There we go, sorry. Go back here to show that breakthrough XAD resin tube that is right here at the end of the sampling train, to basically make sure or assure yourself that you've captured everything that could be captured. So then the question becomes, so Chuck, you kept saying these are for semi-volatile and PFAS. Well, what about volatile PFAS? Because we are talking about air, right? Air sampling and analysis. So first, let's look at our targeted compound list. So this targeted compound list are the ones that are the semi-volatile type ones that can be done as a part of OTM 45. But for the volatile, look at those. Look at the red highlighted compounds down there. The fluorotelmer alcohols and then the fluoroether that we're going to talk about here in a second. So the slide after this has a sampling train based off of a modified TO18 that can be used for fluorotelmer alcohols, and here I just show the 4,2-fluorotelmer alcohol for capturing those fluorotelmer alcohols, as well as these byproduct from the combustion, this fluoroether. It's a tetrafluoroether entity, and which are non-ionic, are neutral, basically neutral. Maybe some polarizable charge you could argue there, but basically a neutral compound. And so their retention and collection and therefore analysis are going to be different than the semi-volatile compounds. So here's a schematic of that setup for that modified sampling train. And a couple differences to point out here is that we're not using an XAD resin in line. And in fact, if you look at the ice bath with all of the impingers there, please note that whereas the ice bath that we were using for the OTM45 was in fact an ice bath, this is a dry ice and methanol bath. So we've got temperatures down to minus 78 for the collection of those impingers. So trying to trap these volatile compounds off of the stack gas effluent. So as a part of this process in stack sampling, we've got concerns, right, over products of incomplete combustion. And so there are a couple of ways, a couple of techniques, I'm going to talk about a couple of those now, that we could employ. And actually, as you might have suspected, they're actually techniques that we're borrowing or reapplying, if you will, from our water and soil type work. And to try and determine the presence of these other products of incomplete combustion, total oxidizable, the top assay, total oxidizable precursor assay, where again in these impingers, collect these impinger samples, and what we've collected either through the OTM45 sampling trains and or the volatile, that modified TO818 kind of collection, basically oxidizing and trying to get an indication by creating or forming the perfluorocarboxylic gases under the same kind of mentality that we would use if we were doing a regular water or soil solid sample for the top assay, and or using a total organofluorine analysis, or really I should probably say combustion ion chromatography, because depending on the process that we're collecting from and where in that sampling train we're collecting and doing the analysis, there's a possibility we may have some inorganic fluoride. So that becomes a challenge and something that's actively being worked on, at least by our folks out of our Knoxville facility, for looking at and trying to distinguish between a total organic fluorine in these collected samples versus any solubilized inorganic fluoride that might have been produced as a part of the stack emission combustion process, and trying to quantify and differentiate between those two, but using combustion ion chromatography for that technique. And then of course also we have available to us the non-target analysis for trying to characterize these products of incomplete combustion. That's where we're using a high-res mass spec. In this case, what we've got shown here is a QTOF, a quadrupole time-of-flight mass spec, to do some suspect screening or some complete non-targeted analysis. Also, truth be told, this same kind of work and information could be gotten off of another instrument platform, one that's manufactured by Thermo Scientific, and that is the Orbitrap platform. So somewhere between a quadrupole time-of-flight mass spec and an Orbitrap mass spec would be able to hopefully do an additional characterization of any of these products of incomplete combustion. From the talk, I mentioned it, I think, a few moments ago, OTM 50, so other test method 50, and that is one I can tell you our folks in our Knoxville facility are working on this one right now to get this set up here. We're using what I think for most air sampling would be a more conventional for more folks. I think this is being sampled into Summa canister, trying to get a whole air or a whole emission, if you will, if that's the right way to talk about it, emission sample, and then analyzing for a select group of volatile PFAS targets. Currently there are 30, I believe, in the method that are listed. So more to come on this. I think this is another part, the OTM 45, the OTM 50, maybe some infusion of a combustion ion chromatography on extracts or samples, trying to basically piece all of these tools together to get to some kind of a mass balance calculation, trying to understand what's going into a combustion process, and then what's being emitted, and collecting all those different fractions and seeing that we're able to capture and account for all that fluorine. So this OTM 50 is going to be one more tool in that tool belt to achieve that. So the last couple things here, because I want to be respectful of our time, looking at PFAS in ambient air. So to date, some of the work that we've done or have been done, and here in this work, our colleagues out of Sacramento specifically did some of this work with a project with TRC, Liz's company, and that is using basically a modified TO13 kind of sampling train using an XAD, like I indicated before, polyurethane foam along with an XAD resin, and then doing some sampling. Of course, there was high volume sampling technique, and that analyzed and reported approximately 40 semi-volatile PFAS, and then of course a lower volume analytical technique for reporting approximate same number of samples. And if you look at the sensitivity range there, that is directly, because they both generate extracts that go to an LC-MS analysis. And so basically your difference in sensitivity is a function of the volume of air that you're able to sample through these cartridges. So what about the volatile area, volatiles in ambient air? And this, I think, touches on some of what the work that Brian was just talking about, and this is these fluorotelomere alcohols in particular. Now, do the volatiles incorporate or encompass some others? It looks like yes, they may, but I don't know that we fully drilled in far enough on all of that. The fluorotelomere alcohols are a pretty quote-unquote obvious application for this, looking at volatiles either in a OTM 50 kind of application, or what I'm going to talk to you here in a second about, which is this modified TO17, which I had on the earlier slide. Here are some examples of where you see and find fluorotelomere alcohols used, as well as acrylate, manufacture of acrylate polymers. I would argue, and we haven't really looked at them that closely yet, but there are some fluorotelomere acrylates and acetates that may also be candidates for taking a look at as volatiles, because at the very least, from an analytical standpoint, you can do those by the same kind of GCMS-MS technique that has been used successfully for these fluorotelomere alcohols. So this VI method for the fluorotelomere alcohols uses a multi-sorbent tube to sufficiently trap the PFAS, the neutral PFAS, uses thermal desorption. And I saw at the end of Brian's discussion, he was going through a lot of this. The analysis is GCMS-MS. So again, I think I say again because I think I bring this up almost every time I do some kind of a presentation, but I think if we have a crystal ball to look into going forward, and this maybe certainly isn't unique to air. I think it's also going to be applicable to water and soil. But when we talk about PFAS, it's not necessarily going to be isolated to just this list of 40 in 1633, or these larger lists that we've done by LCMS-MS. I think it's also going to include some ultra short compounds by an LCMS-MS kind of technique, and this is where I'm coming back around to, it's probably also going to include some neutral compounds that are going to be best done by a GC-MS kind of technique. Now, you can see the kind of sensitivity that Heidi and her crew have been able to get for 4 fluorotelmer alcohols using this multi-sorbent technique. I suspect, and unfortunately, I wish we were all together and in person, because I'd sort of like to talk to Brian about this afterwards, but I suspect that one element of the not seeing the fluorotelmer alcohols, or one possibility, not a definite, but one possibility for not seeing the fluorotelmer alcohols in the soil and the water in the work that he had done may very well be that the analytical technique to date for the fluorotelmer alcohols has been an order of magnitude or 2 higher than we have for our targeted PFAS. So I think as we improve that analytical application and are able to see lower, we might actually be able to uncover some residues of the fluorotelmer alcohols in water and soil, which then might better help to explain what we're seeing in the VI. And then just last slide here to summarize, basically 2 approaches for PFAS in ambient air. The modified TO13 that uses LC-MS solvent extraction. You see there, you can do a high volume sampling or a lower volume sampling, and the lower volume is sort of like, with a personal sampling pump. Get a pretty standard list of PFAS, anionic forms of PFAS. And then, of course, we've got the modified TO17, in part modified because we're using we're using thermal desorption, but we're using a sorbent that is to date, as far as I know, it's a proprietary sorbent. It's a multi-phase, multi-bed one that has been developed and tailored towards good retention for and no background for these fluorotelmer alcohols. And you can see what kinds of achievable limits we've got there. And with that, I'm going to end it so we can get to a question and answer session. So thank you for your attention.
Thank you very much.
I'm going to start with a couple of questions for Chase. So the first one is, did you consider the impact of heat to see if there were reactions or greater release of PFAS?
No, not initially. In our initial experiments on AFFF, we really just use ambient conditions. We are interested in the addition of heat and what that different decomposition of intermediates that creates, but given our budget, we weren't able to get that complex. But that is on our wish list.
Okay. So next question, since AFFF is used in putting out fires, wouldn't testing the PFAS generated from this application be valuable as well?
Yes, yeah, and I guess this is kind of gets that same answer is, that is something we want to look into. I mean, we're still really at the lab phase, trying to tease these things out, and as I think a common theme of today's webinar is there's still some analytical challenges associated with these compounds. So we are trying to keep, the conditions we're testing under fairly controlled at this point, just because, like I mentioned, our initial study, we got some complicated results, seeing PFOA concentrations when we really didn't think we would. So I guess to wrap up, really just trying to keep it simple at this point. But again, that's something we would like to do in the future.
Right. And do we know why you were seeing the PFOA? Is it from transformation of some of these precursors, or?
That's the hypothesis, is that we are driving these less stable compounds to a more stable endpoint during analysis. Now, Brian might have some insight on this, or Chuck, because I'm thinking back to a conversation I had with Heidi Hayes at Air Toxics, and I think the current hypothesis is that is happening during thermal desorption. University of Nevada, Reno has done some follow-up testing, and we don't see PFOA when we remove that thermal desorption step.
Okay. All right. Gary, I was wondering, do we know why like the PFBA, PFOA, the N-methylphos, and the N-ethylphos were showing up as blank contaminants? Do we know where it's coming from? Is it a certain media or?
Well, it could either be coming from the laboratory sorbent or from exposure to the blanks in ambient air. The way we dealt with the field blanks was that they were put in a sampler. So the trap was sitting in the field. The co-located samples were drawing actual flow. The field blank was the sorbent cartridge seated in the sampler, but no flow. So that would suggest that it might be coming from ambient air, because as we showed in the data, PFBA was the highest concentration PFAS compound found in the samples, and that's consistent with what other people have found as well. So it could be laboratory, but I'm leaning towards it maybe coming from actual field contamination.
Okay.
But it wasn't significant enough to interfere with the actual concentrations measured.
Right. Okay. Brian, in the soil and groundwater analyses that you did you test for other precursors besides fluorotelmer alcohols? I'm personally curious because I know fluorotelmer alcohols are sometimes intermediates for the transformation of other PFAS precursors. So I'm just wondering if anything like that was done.
Yeah, we presented the list, and that's what we look for, whether there are other compounds there that might well be. And yes, in the soil environment, I saw another question in the chat from Jaana, are the fluorotelmer alcohols easily transformed? And in the soil environment, yes. If you take, for example, the 8,2-fluorotelmer alcohol and go through various cycles of oxidation reduction, which is what you're going to do with the fluctuating water tables and so on, it can, depending on the path, it can either get down to the down to PFOA or PHEX, depending on whether you're losing or the fluorines and where the bonds are breaking. So yes, it can be. We didn't look at the other ones at this point in time. And then just to go back, if I got a second, go back to Chuck, want to talk to me about that. And I agree, yes, there's detection limits, I'm sure. And on our pilot study, we didn't care to get down to the super detailed stuff. We're looking more for presence and quantifying higher or lower. So yes, Chuck, with your lab doing our soils and groundwater analysis, yes, that's the answer.
Okay. Would top assay be helpful here for like the soil and groundwater, comparing it to the soil gas, just to see if there are, a lot of other precursors in the soil and groundwater?
Yeah, it's possible to pull up the other ones, the precursors, top and things like that, to see whether there's more than what we had, to do a more of a mass balancing type of thing. See, yes, we got them all, or no, we did not. But we were just strictly, again, being a pilot study, we're looking at these compounds and where are they, what's the distribution? Are they in the soil? Are they in the water? Are they in the gas, slab gas? And unfortunately, and one of the things we will do in the next step in the lab test, where we're going out to the field, we're also going to try to grab indoor air, the last of the vapor intrusion pathway steps. It's great if it builds up underneath your slab and whatever, but if it doesn't get any indoor air, do I worry about breathing about it? No. So.
Okay, thanks. Chuck, so your lab's doing the OTM 45. I was curious how often you see breakthrough on the XAD.
I don't know that they see it to the back one all that often, Liz. I mean, they're definitely seeing stuff in all the condensers condensate, but they generally, most of the stack emissions are relatively well characterized before they go in and do a full sampling. They sort of do a snapshot, a quick sample on XAD, get an idea of general mass, and then set up the formal OTM. Since the OTM 45 is so, I mean, you're talking, I think, one event just to collect the sample is in the $20,000 to $40,000 range just to get it collected, and that's not even doing the analytical work on it. So it's a big investment.
Yeah. There's a question here for you. Does modified TO17 method employ isotope dilution technique?
Yes, she's using a couple of labeled FTOHs, and I believe as a way to introduce, or is introducing those into the tube just prior to the thermal desorption. She had been working on that. I don't know all the details on that, but her intention, Heidi's intention, was to incorporate some of those C13 labeled FTOHs like we're able to use for the water and soil analysis.
Okay. So I have 3 questions on this, and I'll open it up to any one of you that would like to answer. And it's about landfill gas emissions. Do we think landfill gas or other anaerobic digesters creating renewable natural gas might contain PFAS, given that they're typically based upon waste products, which often contain PFAS? So what maybe what you're seeing or thoughts?
Yeah, I'll take the first stab here for a second. We did look at a landfill, a closed municipal solid waste landfill here in the state of Georgia, and we were seeing some of the PFAS in that gaseous phase there, whether they were in the methane vent well, the vents that are coming up off of that, as well as a little bit in the soil, but it's preliminary for us. So they're possible. I haven't done anything further as far as studying that in greater detail. So I'll turn it over to Gary, whoever.
Yeah, there are a number of publications out there that show PFAS in landfill leachate. So it certainly would be obvious that it's going to end up in the air as well. So I think, and the fact that things have been deposited in some of those landfills for decades and decades, and the PFAS is going to still be there. So yes, I think it would be very, very likely that you're going to see PFAS in air emissions from landfills.
I think Liz, was it Steve from Sanborn Head? I thought he had I think he had a publication from like maybe 3 or 4 years ago, where they had done some rudimentary collection of air, I believe, and found FTOHs.
Yeah, that's Steve Zemba.
Steve Zemba, thank you.
Yep. Okay.
I was just going to add that there have been a couple studies on ambient air quality above municipal solid waste landfills, and typically the fluorotelmer alcohols are present above what you'd see in a city background concentration. So they're there in the air, and then there is a study out of Oregon State just recently which quantifies fluorotelmer alcohols in landfill gas.
Okay, great. Given the state of testing methods and difficulty with things like contamination, like we're seeing, what challenges do you anticipate, or do you know maybe any states that have experienced any challenges with air standards for PFAS? We've only got a few states right now with standards, but...
Yeah, to be clear, there was an earlier question, Liz, that I wanted to answer. Those concentrations that I showed, and I think Chuck showed, are fence line concentrations. They're modeled concentrations, so they're not in stack. And I want to distinguish that between, differentiate between that and air emission standards, which would largely apply at the stack side. I think we're not there yet to establish standards, and I'll go back. I forgot who it was that mentioned it. We don't have the toxicology of PFAS relative to the inhalation pathway. And so creating firm standards at the source, we're just not there yet. I think, Chase, you said that multiple times. And it's going to take years. It just is.
Right.
Yeah, I was just add, as I was hammering on in my presentation, the lack of inhalation data does present a challenge. Some folks have gotten excited about our data, or they've talked to me about Brian's data about this potential for VI. But there's 2 things that we kind of hurdles we need to meet. One is, are these chemicals vapor forming? But the second is, do they pose an inhalation toxicity risk? And that's where there's just not enough data yet. Travis Klein at Geosyntec Consultants a couple years ago did a route-to-route extrapolation to come up with some numbers. I'd be happy to, that's a presentation I co-authored with him. I'd be happy to pass that around if anyone's interested. But I think that's the closest we've come to kind of trying to come up with some sort of risk-based number for some of these compounds, particularly for a vapor intrusion situation, which I'm, of course, interested in my line of work. So anyways, I'll just leave it at that.
Okay, great, thank you. Does anybody know what data is available relative to air emissions from wastewater treatment plants? Or know any good references for that? Maybe not. Okay.
No.
Okay.
I can tell you, Liz, that we're looking at the biosolids issue, and both MWI, municipal waste incinerators, and sewage sludge incinerators do not generally operate at temperatures needed to affect significant PFAS destruction. And so while it wasn't specifically talked about from wastewater treatment plants, if that wastewater treatment plant then treats its biosolids in a sludge incinerator, it's likely sending the PFAS right back into the air pathway.
Okay. Okay, here's a comment or a question, maybe for a couple of you. The Parkersburg, West Virginia particle size distribution has been used for deposition modeling because it is one of the few sources of such data. However, it's not based on source testing, but on fence line measurement. So doesn't this severely limit its utility for deposition modeling of stack emissions?
His statement is correct. In the case study I presented, we actually had the particle size data that we used was from the stack emission. And yes, it's limited. I think the purpose of the particle size data in the ambient network was to compare from a mass perspective how much, almost like on a material balance basis. If the plant is emitting X and we captured Y of these sizes, what does that represent in the total of the total? Gary, you were talking, I think you were correct. They used the cascade impactor for particle size differentiation. Do you see it the same way?
Yeah, and that was in the ambient air, so that they were analyzing the fractions from the cascade to correlate the concentration of PFAS found on that particular fraction. I don't know whether you can compare or assume that that represents the stack emissions. Probably not a good assumption, but they were using it for a different purpose.
Right.
Okay. I'm not sure who this question's for. Were these stack tests done in sources with PM controls? Is that particulate matter?
Don't know.
Or are there any studies on how the PM pollution control devices affect stack PFAS emissions?
Well, I will say, if it related to my presentation, we talked about this earlier, that the presence of spray booth filter reduced the size of particulate and hence the load of PFOA in my example to the atmosphere just by its sheer presence. The resulting particulate, therefore, were very small in size, diameter size, which would be expected. On the pollution control side, I think it's worth noting that Chemours in North Carolina, pursuant to consent, put on a thermal oxidizer. And even though this stuff behaves as a particulate, as we talked earlier, the thermal oxidizer is capable of destruction of both vapor and particulate phase. I think that's an important point to make. When we get to the point where we're controlling these sources, technologies like that, unless you understand what phase it's in, are going to be the method of choice.
Okay. Okay, let's see. So Chase, did the results of your experiment show that the Henry's Law is an appropriate method for estimating PFAS release from the AFFF headspace?
Good question. I would say not yet. That's where these analytical methods come in to, validate what we're seeing from models. So we're able to take those Henry's Law constants. I mean, this is just very simplified, just the partitioning from water to air. Now, that gets a little more complex when you get into the vapor intrusion pathway. But we really haven't been able to validate that with field data yet. I think that's where the development of this modified EPA method TO17 comes in. But yeah, unfortunately, don't quite have that nailed down yet.
Okay. Question for Brian. Just where is EPA and the PFAS strategic roadmap with vapor intrusion and regulations and studies?
No. Okay, I was waiting for more. That's abroad. We have the PFAS roadmap is out there. We're working through it. It's a multi-year plan. Things that came up here on the call today, for example, I know we're about to update, they're working at least this fiscal year, OTM 45 and OTM 50, the other test methods. I think Chuck might have brought up the names up there in his presentation. So we're moving along in all aspects. EPA's research includes both looking at methods, looking at the risks involved, and looking at various removal projects going on, whether it's thermal or whatever the case might be. So all I can say, not knowing the whole breadth of everything that we do, we are moving along on that roadmap and making progress in various areas across the whole board of PFAS.
And that includes vapor intrusion?
Yes, I'm the vapor intrusion side with Chase and so on. And yes, we're looking at that too. And the OLM, the Office of Land Emergency Management, was interested in that because they're the ones who put out the vapor intrusion guidance for volatile organics. And now they're looking at, like I say, the question is, do we have to worry about the volatile PFAS as well?
Right. Okay. Chuck, can you tell us what the GCMS-MS offers that the GCMS doesn't? We normally use GCMS just for our other organic contaminants. So I just wanted to make sure everybody is clear on why GCMS-MS is important.
In general, the GCMS-MS, this isn't universally true. It is somewhat compound dependent, but the GCMS-MS will give you're able to monitor its unique transitions, mass transitions that even using selected ion monitoring by single quad technology doesn't give you that uniqueness of detection, as well as that platform has a lower noise in the signal response that comes out. So then your effective signal to noise is better than you have in a single quad mass spec. So it generally lets you get to lower levels. For example, although this is, I guess, is a great example because it's not comparing GCMS to GCMS-MS, but even just my comment to Brian about the sensitivity in the soil and water, part of the reason why I brought that up too is because our original technique was set up on a GCMS-MS that was, before we replaced it here this last year, it was like 12 to 15 years old, somewhere between 12 and 15 years old. And we put it on a new platform and did some optimization on that new platform. And we're probably going to be able to report out like
high single digit and low double digit kinds of RLs for the fluorotelmer alcohols, a nanogram per liter, in a water. So it puts it into the same ballpark as your LCM SMS analysis without going to extracting 2 liters of water or something crazy like that, right? So that's part of what that GCM SMS platform will allow us to do. Could you get there with a single quad? Maybe, but you'd have to do a whole lot of extra work to try and get down to those kinds of levels.
Okay, thanks.
Yep.
Gary, where field blanks had detections, did laboratory method blanks show similar detections? And also confirming what you said earlier, are the field blanks collected passively in the same location as the actively collected field samples?
Yeah, with respect to the last part of that question, in the photo I showed, we had the 3 samplers set up. One of those was the field blank, and it's basically in the same location or within approximately the same location as the samples themselves. With respect to contamination, we find contamination both from the laboratory and the field. I mean, it's a mix. You can't say that it's limited to one or the other. But I think the PFBA that I spoke to earlier probably was coming from the field because of the concentrations in the air and the passive collection over 24 hours, 72 hours. But there's contamination from everywhere. I mean, and you try to control it, and you can't completely eliminate it. I don't know what Chuck's feelings are on this, but you can't completely eliminate it.
I agree with you 100%, Gary. You can't completely eliminate it. You just need to have some control and some processes in place so that you understand where it's coming from. Even the example you gave with the PFBA, we have colleagues that have reported when they changed out a mini split HVAC system in a laboratory, it was contributing PFBA to the air in the lab. They saw their blanks go boom way up. These were water blanks, and that was the only change. And it was only after they stopped operating that mini split, purged the room, that they could see that the PFBA level went down. So they're quite ubiquitous. So it's all about monitoring and recording where your sources are.
Yeah, you have to have a lot of controls: method blanks, field blanks, strip blanks. If you want to get a handle on it.
Yes, sir.
Right.
Yep.
All right. I think that's going to do it for the panel. So thank you to the speakers. Really, it was a wonderful workshop all around. And thank you to everybody that attended. I hope you enjoyed it. So.
Thanks all. So one final thank you again to our incredible speakers. Thank you for organizing this, Liz and Jaana. This is just a quick reminder for those of you who are still on the call and being mindful of your time. We will wrap things up. There is a webinar feedback survey link in the chat. This is very, very brief, but incredibly helpful for us at EBC to have your feedback, especially when we are asking about other future topics you would like to hear more about. So if you have a moment, please go ahead and fill that out. Also want to let everyone know that all available speaker presentations from today will be posted to the event page on the website. I will try to do that as soon as possible. We will also follow up via email with a link to the recording of today's webinar and a link to those presentations. And that typically takes us about 5 days just to make sure that we've edited up the recording nice for all of you. And if you have liked what you've heard today and want to get a little bit more involved with EBC, if you're considering membership, please reach out to any of the EBC staff, and do keep in mind that the program planning meeting for the Emerging Contaminants Committee, so if you want to talk more about all things PFAS, that will be on July 13th. Registration is open for that. That is exclusive to EBC members, so that is a nice member perk, but then you get to have an active role in planning things out for the next 6 months. And thank you again to all of you for tuning in. Thanks to our speakers. Thanks to Liz and Jaana. And I hope all of you have a great rest of the day. Bye.
Okay, thank you.